In order to answer the big questions, you'll need to have the right data, arranged in the right way. BigQuery is the main Google repository for data that will be used in analysis and machine learning. In this course, I'll navigate the BigQuery UI and CLI, explore public datasets, and learn the art of dataset replication. I'll cover the process of creating robust datasets, delve into the world of BigQuery tables, views, routines, and connections, and uncover the capabilities of BigQuery search and vector indexes. I'll also help you gain proficiency in importing data, batch loading options, and publishing datasets for collaboration. The course will guide you through optimizing costs with various pricing models and introduce you to Looker and Looker Studio, where you'll be able to create and share insightful reports. Finally, I'll help you equip to troubleshoot with both BigQuery and Looker, ensuring a smooth data analysis experience. This course is one of a collection that prepares learners for the Google Professional Data Engineer exam. In this video, we're going to describe the use cases for implementing BigQuery and its basic architecture for storage and analytics. BigQuery is just a fully managed AI-ready data analytics platform. This means that it helps us maximize the value from our data, and it's designed to be this multi-engine, multi-format, and multi-cloud system. I can store 10 gigabytes of data and up to 1 terabyte of data of queries for free per month. So that's very powerful. So imagine being able to store 10 gigs of data and you can run up to 1 terabyte of queries for free. And you can get all sorts of different credits when you start off with Google Cloud and BigQuery. But this multi-engine, multi-format, multi-cloud process is what's going to make it very easy for us to leverage Google SQL inside of BigQuery so that we can retrieve this data. So here's some of the key features in BigQuery. We can use Gemini in BigQuery itself. So this provides an AI-powered assistive and collaboration feature set. It has things like code completion, code assist, visual data preparation, and intelligent recommendations that helps us write our queries inside of the console, and it just helps us to enhance productivity and optimize costs. And you'll notice that BigQuery itself will use a single unified workspace that includes SQL. It even has a notebook and kind of system, so that if you're familiar with things like a Python notebook, you can run these kind of SQL notebooks deals for data practitioners of various coding skills to simplify our analytic workflows. We can use multiple engines on a single copy of data. So if we're looking at serverless Apache Spark, for example, it's available directly in BigQuery. So I can write and execute Spark in BigQuery Studio, and I can export our data or manage the infrastructure there. And I can use things like BigQuery Metastore, which will provide a shared runtime metadata for SQL and even open source engines. And I can use multiple engines, including things like SQL, Spark, Python, and I can run this on a single copy of our data and metadata. And I can break my data into silos, and I can even increase efficiency this way. And data in open format management is important. So use BigQuery to manage all types of data across multiple clouds. We can use things like unstructured data. We can use fine-grained access controls. And we can also use the built-in machine learning models. So BigQuery ML provides built-in capabilities to create and run machine learning models for our BigQuery data. And so this is where I have a broad range of models for predictions and even access to the latest Gemini models. And I can use those models to derive insights from all sorts of data and data types. And I can even use it to create some generative AI tasks such as text summarization or text generation, or I can have something like a multimodal embedding or even a vector search process. Here are some key features, again, of BigQuery. So it has integrated data governance, which is important. So this is built into BigQuery. It includes integration of like what's known as Dataplex capabilities, such as metadata catalog, data quality, lineage, and profiling. And we can also use enterprise capabilities, so such as cross-region disaster recovery, which provides a failover procedure in the unlikely event of a regional disaster. And it even has data backup and recovery features to help us recover from user errors as well. Real-time analytics with streaming data pipelines. It can ingest streaming data and make it immediately available to query and integrate for streaming products like Dataflow. And this allows us to accelerate query performance and reduce costs with BigQuery's materialized views built in. So I can have these continuous queries that are updated as the data is being streamed into the table. I can even build in business intelligence, so it allows me to share those insights with the business intelligence team. So I can create and share insights in Looker Studio, and I can build these dashboards that go beyond like business intelligence. I can analyze billions of rows of data inside of BigQuery, and this is all done here in the Looker Studio. Here's how the BigQuery architecture is laid out. So it consists of two parts. First, we have the storage layer, and this ingests, stores, and optimizes our data. And then we also have the compute layer that provides analytics capabilities. Now, these two layers will operate independently of each other, and this is all done by Google. We don't actually have to set this up. We can actually use legacy databases that have to share resources for read and write operations and analytical operations. And what you'll find us in those legacy databases is that you'll get some type of resource conflicts and you'll get slow queries while data is written to or read from storage, because it can only do a few actions at a time. Now, BigQuery's separation of compute and storage layers allows us to dynamically allocate resources without impacting the performance of or availability of the other layer. So if I need a lot of computing power, it's not necessarily going to affect anything on the storage layer. Or if I need more storage, retrieve a lot of information from the storage layer, it's not going to affect the compute layer. So they're independent of one another, and that's where the superpower of BigQuery comes in. And this just helps us load, process, and analyze our data so we can inform critical business decisions in a timely manner. Now, here are some of the use cases that we've used BigQuery before. So we can upload data from any source. So I can make analytics easier by bringing together data from multiple sources into BigQuery. So this is where I can upload data files from local sources. We've got things like Google Drive, cloud storage buckets, BigQuery data transfer services, cloud data fusion plugins. There's so many different services that you can actually just ingest data directly into BigQuery. We can also migrate our data warehouses into BigQuery. So I can use Google Cloud's enterprise data warehouse. So I can streamline my migration from things like Oracle or Redshift or Snowflake to BigQuery using this free and fully managed what's known as the BigQuery migration service. And that's a service that's designed to just transfer all of our data warehousing tools that we already have in place and another vendor into Google BigQuery. I can also unleash generative AI use cases with BigQuery and Gemini models. This is really powerful because not only am I storing my data in one central repository, but now I can actually use Gemini and Vertex AI. And this model is designed for higher input and output scale, and it results in better quality across a wide range of tasks. So I can do things like summarization or sentiment analysis on the task, and that's just all built into the Google BigQuery. So I can just imagine being able to run a few functions on a column of data that contains text and ask it to do sentiment analysis on that column. Well, you can do that very easily. And you can access it using simple SQL statements, or I can use the BigQuery's embedded data frame API from right inside of the BigQuery console without having to do very much. It's there for me to import and use. I can also do what's known as event-driven analysis. So I can gain a competitive advantage by responding to business events in real time. I can use this event-driven analysis. So built-in streaming capabilities will ingest this streaming data and make it immediately available for me to query. And it allows me to stay agile, make business decisions based on the freshest data. I can gain some insights from images, documents, and audio files. And this unstructured data represents a large portion of untapped enterprise data, and it can be challenging to interpret, and it makes it difficult to extract meaningful insights from it. So I can leverage the power of what's known as Big Lake, and I can derive insights from images or documents or even audio files themselves. And these AI models are built in, including Vertex AI's vision, document processing, and speech-to-text APIs, which are all built into the Google ecosystem here. And I can even predict business outcomes with leading AI ML systems that are built into BigQuery. So BigQuery ML will use machine learning by empowering data analysis to build and run models using existing business intelligence tools and spreadsheets. And this is where I can use predictive analytics that can be used to streamline our operations, and you could boost your revenue or even mitigate risks. And it can guide your business decision-making process across the entire organization just by using this product. Another use case that I've used this for is a big one. It's log data analysis. So if you have an application running in the cloud, it's going to be generating some log files. Well, what we can do here is we can analyze and gain a deeper insight into this logging data with BigQuery. I can even store, explore, and even run queries on this data coming from our servers or sensors. It could be anything. So if you have an API, for example, it's generating some log files. You can ingest those log files into a BigQuery table, and you can query your log file. You can basically do some analysis on that, figure out, hey, have I seen any server 500 errors in the last 24 hours, things like that. And I have privacy-centric data sharing. So I can create a low trust environment, and I can have my partners to collaborate. And this is where I can copy without copying or moving this underlying data. And it's all done within BigQuery, so I just give access to that data, and it doesn't have to move from the location. It's just people can have access to it. So it allows me to perform privacy-enhancing transformations using BigQuery SQL. And one thing we can also do is we can improve marketing return on investment, or ROI, and our performance. So we can bring the power of our Google artificial intelligence tools for marketing data, and I can unify marketing and business data sources in BigQuery. Now I get a holistic view of the entire business. I can increase my marketing ROI. I can address performance using the data that I've collected on things like the ads that I've put on, the digital advertisements I'm putting on, and I can deliver personalized and targeting marketing at scale with artificial intelligence built in. And that is how we can use and leverage BigQuery, as well as just the BigQuery architecture and some of its key features. In this video, I'm going to show you how we can actually query some public data sets inside of BigQuery. So to get started, let's go to our Google Cloud Console webpage here, and let's actually look for BigQuery up at the top in the search bar. And you'll be met with an icon that looks like a magnifying glass, and it should say BigQuery Data Warehouse / Analytics. Go ahead and click that, and you'll be met with this page. Now, from here, this is our central hub for actually anything BigQuery. And what you're looking at is a way for us to actually start writing queries, SQL queries, or create a Python notebook, or create a data canvas. What we can do is we're interested in running an SQL query, so we'll go ahead and click SQL, and we'll be met with a page that looks like this. In here is where we're going to be writing all of our queries, our SQL queries. And these public data sets are available for us to query, and you can find more of them very easily, and I'll show you how to do that in just a second. But let's go ahead and just write a basic query so that we can analyze the public data set for USA names from 1910 to the current year. So let's go ahead and write a simple query. So we're going to write select. If you're familiar with any type of SQL, this should be pretty straightforward here to understand. So select name, comma, gender, state. Let's go do that. Let's go year, and let's go number. And what we're going to do here is we're just going to write from, and we're going to use the backtick command. Now the backtick is what's actually going to let us know what the name of our data set and table is. So the data set that we're interested in is called BigQuery-data.usa_names.usa_1910_current. And that's it. Then we close a backtick. Now what I want to do is I just want to find where the state is equal to California. So I want to find the top 10 names in the state of California in the year 2000. And we want to just order it by descending. So let's go and year is equal to 2000. We'll order by the number count, I guess, for the number of names. And we'll limit it by 10. Now this is a common query that you'd write. And if we click run at the very top of our page, you can see right here that we have the top 10 names in the year 2000 in California. So we can see here that these are male names. These are the top ones in the year 2000. We can actually do the same kind of thing and go and gender, and we'll set it equal to female, or F. And we'll see the top 10 women names in California in that year. And you can see right here that it's Emily, Ashley, and this makes sense. So there we go. So that is how we can write some queries inside of the console Let's see how can we find more public data set names. Exactly where did I find this name of our data set? Well, if I click this little sidebar window here, the Explorer page, and I'm left with all of the data sets that I have access to on the left-hand side. And if I click Add up at the top right, a little window will pop up. And if you come over here, you can search for data sources. So there's plenty of different data sources that I can search for by name. But if I scroll down here, there are many different options that I can use as a data source. One of them is known as public data sets. You can look for this icon right here. If I keep scrolling, it says BigQuery public data sets from the Google Cloud Public Data Set Program. Let's go ahead and click that. Now I'll be left with some categories on the left-hand side. So there's analytics, and there's maps and different data sources that we can use. Let's go ahead and search for FAA and see if this pops up for anything. And you can see right here there is some data, and this deals with, let's see if we can find some more data sets. So this deals with NextRad level 2 data. So there's different categories that we can actually work with, either climate or science and research. If I come back here to the marketplace, I can search for more data sets this way. But let's go ahead and come back and let's look at some more data sets that we can query. So again, if I click Add on the top, come over here, scroll down to public data sets, and if we scroll down just a little bit further, there's many different ones that we can use. So let's go ahead and click Cloud to Ground Lightning Strikes, and we can explore this data set. Now I can click View Data Set, and it'll open up in a new tab for me. And this data set now, you can see that there's in my Explorer window, there's a new set of data that's open called the BigQuery public data. And this is where I can actually explore the data set that I want to query. So there's one on COVID-19, there's one on crypto. If I scroll down a little further, you can see the one I have selected is called NOAA_lightning. If I click the little drop down menu, I can see the lightning strikes. And here's one where I've got just some dates, a number of strikes. It tells me what's inside of the table here. So these are all columns and the different types for those columns. Now I can query it, but here's another one that's interesting is the FAA. So this is dealing with aviation. This is talking about US airports here. Again, there's a few different columns here with their own names and types. Now, if I click the query command up at the top next to the name of the data set, after I've clicked the table, and it gives me an option to open and query this data in Data Canvas or a Python notebook or in a new tab. Let's go ahead and query this information in a new tab. And let's go ahead and type select star, and let's look at some airports inside of the US. So again, this is now filling in my public data set name for me. And I can click Run to run this. Now, I didn't need to actually find the data set in the marketplace for me to do this. If I knew the name of the data set, I can just use it directly inside of BigQuery. But this is just a way for you to explore what's available publicly on BigQuery to retrieve any data sets that you're looking for or anything you're interested in. And so right here, you can see I've just selected the 10 airports. You can see that there's an FAA identifier. There's a name for it. It even gives me a latitude and longitude, as well as an airport geometry. It gives me the elevation, different identifications for the airport, and where it is, what city and state it's in, what country it's in. So there's so many different data sets that we can actually query like this. And it's up to us on how we choose to explore it or what we do with it. But this is just really leveraging the power of BigQuery to be able to write our queries this way and then immediately get results in a way that's easily comprehensible. And now I can save those results or explore them in another service if I choose to. So that's a little bit on public data sets and BigQuery. In this video, I'm going to demonstrate some of the tools that are available in the Google Cloud Console for the UI and managing our BigQuery user interface. So what you're actually seeing right now is the BigQuery user interface, and it kind of looks a little overwhelming at first, but there's a few main components that help us understand what's happening inside of BigQuery. So the first thing I want to talk about is the pane on the left. This is called our BigQuery Explorer. Now, the purpose of this is just to allow us to explore our data sets, our tables, and our views in our individual projects. So if I click this little arrow here, we can see that there's a few different things called queries, or shared queries, or notebooks, and there's all sorts of data that's inside of these that allows me to explore what's actually stored in my projects for Google BigQuery. I can view the table schemas and metadata, and I can even preview data within our tables. Now, what we want to do is I can even use the search bar here to quickly find data sets and tables that I have imported into my projects. Now, in here on the left, on the right here, is the query editor. Now, this is just so that we can enable writing and editing some of our SQL queries. It features things like syntax highlighting, which is what you're seeing here. You can see that the syntax for tables are green and they are underlined to let me know. Integers and are highlighted red. All the keywords are highlighted blue to let us know that these are actual keywords for SQL. And so it has autocomplete for these keywords, it's table names, and even column names. What's interesting here is that I also have a query history or job history. If I scroll to the bottom of the page, you should see a job history icon that sees all of my queries that I've written in the last little bit, and it gives me a way for me to actually click the query and actually rerun it if I need to. So it's not, there's a detailed record of what I've run on BigQuery. And I can even save queries for future use. But what's interesting here, if you see this little button is called schedule, I can set the query to run on a schedule, say every day at 3 o'clock, for example. And I can run this query all the time. So this is really useful if I'm trying to run things at regular intervals or at certain times. And what I can do as well is I can even show you the query results page, which is what you're seeing here. Now I'm just going to move this bar a little bit higher so that it's easier to see. But this is the query results page. When I run a query, this is the actual table or the output for the query, and it's shown here. And I can see it in different formats, such as JSON or CSV, or I can even export it to Google Sheets if I click Save Results. And there's different ways that I can actually save this information. I can even copy it to the clipboard if I choose to, and paste it somewhere else if it's small enough. Another thing that is quite useful here is, and it's not shown on this page right now, but it's called the data transfer service. This automates our data transfer from external sources into BigQuery, and it can set up our scheduled data transfers from Google products such as YouTube or Google Ads, and even other cloud services, and I can monitor the status of data transfers. I can access it via transfers in our left navigation page. If you look over here to the left, you should see a section that says transfers. And this is where I can actually, like data transfers right here, is where I can actually move data from one location to the other. And I can set up a new data transfer in this location. And all of these services are the primarily components of our UI for BigQuery. And it's useful for what we're trying to get done. But the more you work with it, the easier it becomes to use. So it's all just about practice. So I encourage you to jump on to BigQuery and try querying some public data sets and seeing how you can actually write your queries and save them and schedule them if you need to. In this video, I'm going to select an appropriate method and have regional or cross-regional replication and when to use one or the other when we're using BigQuery data replication. Let's first understand what it means to have a cross-regional data set replication. So data set replication is I can set up this automatic replication of a data set between two different regions, or what we refer to as multi-regions. And what this means is that when I create a data set in BigQuery, I can select to be a single region or two different regions or a multi-region where the data is stored in multiple places in a large geographic area that contains two or more geographic regions. Now what happens is when I have two or more geographic regions, I now have a backup to my system. So rather than have it in a single region and maybe the power outage goes in that whole region or something happens there, I have now a backup so that it's there for fault tolerance, but it's also there to query information from different places. So if I have multiple regions, the same data hosted in multiple regions, anybody can access this BigQuery instance and retrieve it in low latency. So BigQuery always stores copies of our data in 2 different Google Cloud zones within a region. And a zone is just an area for Google Cloud resources within a region. So typically every region has 2 zones, and so data copies are always stored in those 2 zones within a region. And if I have it in a multi-region place, replication between zones will use what's known as synchronous dual writes. So when I write to this BigQuery instance, what I'm doing here is I am replicating that write between those zones, and this is what's called a synchronous dual write. The write is not finished until it's written to both zones. So that's what happens in a single region. Now, BigQuery and geo-redundancy can replicate any data set, and BigQuery just creates a secondary replica of our data set and it sends it in a different region that I specify. And then the replica is then asynchronously replicated between our zones, and so I can have a total of 4 zonal copies across 2 or more regions. Now, data set replication has what's known as a primary region. This is when I first create a data set. BigQuery is going to place the data set in this primary region to start. And then there's the secondary region. So when I add a dataset replica, BigQuery will place the replica in this secondary region. Now, the replica in the primary region is that. It is a primary replica. And the secondary region is what's known as the secondary replica. Now, the primary replica is writable, and the secondary replica is read-only. And writes to the primary replica are then copied over and done asynchronously to the secondary replica. And so that happens within each region, so that data is stored redundantly across 2 zones, so that if one thing happens in one zone, well, no problem. We have another zone that can turn from the secondary replica into the primary replica temporarily while we bring everything back up in the primary region. So here are some key considerations when you're thinking about replication. Locations and co-location is really important. I can replicate data across regions, and so the data is just going to be located only in the locations where the replicas were created. And for replicas that require co-location, and this is something that could be used as views or materialized views, you can add a replica in a location that is different from or not compatible with the source data's location. And this is important that we don't introduce any errors there. Another thing that we have some limitations here, the BigQuery dataset replication there are some limitations to these things. One of them is the data streams that haven't been committed or not replicated in the secondary replica if a table is written to with the BigQuery Storage Write API. So replication of streaming data from BigQuery Storage Write API is best effort and may see high replication delay, so it's something to keep in mind. You could have tables that are injected through data stream to BigQuery by using change data capture. That's not supported. There's a few different limitations as well that we'll go into, but one of the things is that you are limited to a maximum of 4 replicas added, then dropped to the same region per data set per day. So there's things like that. You can't just infinitely replicate your data, but those are really the pieces here. There's also, how do we handle outages? So cross-region replication is not intended for use as disaster recovery plan. In the case of a total region outage, what we'll notice is that the primary replica's region, you cannot promote the secondary replica. So this secondary replicas are read-only, and you can't run any write jobs on the secondary replica. And you can't promote the secondary region until the primary replica's region is restored. So this is something that you have to think about. This is just meant as something to reduce latency rather than have some type of disaster recovery in place. Okay, so that's a little bit about some key considerations when it comes to replication in BigQuery.
In this video, I'm going to show you how we can actually create a data set in BigQuery and talk about some of the options that are available when we're creating our data set. So let's get started by going to our Google Cloud Project console and searching for BigQuery up at the top in our search bar. And you'll be met with the icon for BigQuery. It'll look like a magnifying glass that says BigQuery Data Warehouse /Analytics. Go ahead and click that, and you'll be met with the BigQuery Studio page. That should look something like this. On the left-hand side, underneath the Explorer section, you should see all of your project's data. Now, the project that I have open is called Valued Bvoke, and what we're going to do here is we are going to click View Actions, and this little 3 dots right there is going to pop up, this is going to have an option there that says Create Dataset. Let's click that. And now we're going to be met with all of our stuff on the right-hand side underneath Create Dataset. It tells us what project ID we're creating this dataset for. And what we're going to do is now just talk about some of the options that are available. So the dataset ID here is just a unique identifier for the dataset within our project. And we just want to choose a meaningful name that is useful for us. And so the one that I'm going to use is called sales data. Let's just call it something like this. So sales_data. And now what I want to do is I get to actually choose a data location. Now this data location, or the region, it's like a location type for this. I can actually say, where the data is going to physically reside. So I can have it set to the United States, multiple regions in the United States, or a single region within the US. Now it's cheaper to have it in a single region for our purposes. So I'm going to go ahead and click region, and then I can choose a single region such as Toronto or Iowa or Columbus or Dallas, anywhere I choose, or I can have it set to a multi-region, and then I can have either the US or multiple regions in the European Union. I'm just going to click the United States for now. And now what I can do is then talk about what's called a default table expiration. Now you can hover over the little question mark here and it'll tell you what this is. The default table expiration just sets a default expiration time for tables in the data set. We usually use this option if we want to automatically delete tables after a certain period. And this can help manage our storage costs and comply with data retention policies. That is quite useful. So for now, I'm just going to actually just leave that disabled, but I can enable it and then say, okay, the maximum number of days for the table. I can say, every 10 days, we want to delete this table information. That's just a way for us to make sure that we are in compliance with policies. Now, another thing that we can have are things like our tags or our labels. That just allows us to manage our policies and our resources in a unique way with the unique tag ID so that I can actually apply these policies to the tag themselves. And that's pretty much it. There are some advanced options that deal with encryption, but you're most likely just going to leave it as a Google managed encryption key. You can have case insensitive table names if you'd like, or you can have it a part of a default collection. These are things that are outside of the scope for this video for now, so I'm just going to leave them as their default. But if you come over here and click Create Dataset, your dataset will now be created, and you'll see it pop up right underneath the name of our project. I call it Sales Data, and you can actually see here, if I click the name of my dataset, you'll see all of the metadata that's associated with that dataset, and I can start adding information to it if I choose to. So that's how we can actually create a data set inside of our BigQuery instance.
In this video, I'm going to describe the structure and use of tables and views in BigQuery. So let's understand exactly what a BigQuery table is. So a BigQuery table contains records, and they're organized into rows. Each record has a set of columns, and we call those columns sometimes referred to as fields. So every table is defined by what's known as a schema, and this describes the column names, the data types in each column, and just other metadata information about the table. I can specify the schema of our table when it's created, or I can create a table without a schema and then declare the schema in the query job or the load job that actually populates the data as when I insert information into the table. Now, how do we create these table names? Well, we want to use the format for project dataset table. So when we actually create our table names, there's a convention that we should follow. And it starts with our project name that we have created in the Google Cloud project. Then it's followed by a period, and then the name of our data set, then followed by another period, the name of our table. And this is how we can access the Google SQL data table best practices. So that when I name my tables these things, this is how I can reference them. Another thing that I can do in the command line is the same kind of thing, except the project name is first, followed by a colon, then a dataset name, followed by a period, and then a table name. And this is what I can use with what's known as the BQ command line, which is a command line tool for the Google Cloud platform in the CLI, and it is just for BigQuery command line functions. Now, there are certain table types that I want to talk about. There's three of them. The first one I want to talk about is your standard tables. These are your standard BigQuery tables, and they contain structured data, And they're stored in BigQuery storage in what's known as columnar format. And they could have many different types. For example, I could have a table which has a schema, and every column in the schema has a data type. I can have table clones, which are lightweight, writable copies of other BigQuery tables. And they only store the change between a table clone and its base table. I could have a table snapshot, which are point-in-time copies of tables. And these are read-only, but I can restore a table from a table snapshot. So it gives me a little save point if I'm trying to change something. There's also something known as an external table. Now, these are stored outside of BigQuery storage, and they refer to data that's stored completely outside of BigQuery. So I can have something such as an external data source, where I can use something known as Amazon Simple Storage Service, or Amazon S3, or Azure Blob Storage, or Cloud Storage in Google Cloud. These are outside of Google BigQuery, and they're referred to as Big Lake tables, and they reference structured data that's stored in data stores. Now, we'll notice is that there's also something known as views. Now, views are logical tables, and they're defined by using a simple SQL query. They include a few different types, so there's two types of views. There's views, which are logical tables, but they're defined using SQL queries. And these queries will define the view, and they'll run each time the view is queried. So it's a lot of computational power. A materialized view, on the other hand, is similar to a view, except they're pre-computed views that periodically cache the results of the view query. And these cached results are stored in this BigQuery storage. So regular views are computed each time you query the view, but they don't take up any storage. And materialized views are pre-computed, and they do take up storage. So there's a bit of a trade-off between when to use one or the other. Now, BigQuery views are just a virtual table that's defined using an SQL query. And I can use these views to provide a reusable name for a complex query, or I can have some type of limited set of data that I can then give other users access to it. So I can give them a slice of the data that could be made of several different other tables. Once I create a view, a user can then query the view just like as they would any other table. And this provides this reusable name for complicated queries, and these can create a limited set of data so that other users can access them. Let's go ahead and take a look at how these typical uses for BigQueries are viewed. So we have this simplified query use. Take a look at this. So by using these BigQuery views, no longer do I have to join 4 or 5 tables every time I need to compute something. I can create a view of those 4 or 5 tables joined together, and then I can just query that view, and that join is now done. And I don't have to do it over and over again. Better yet, I can actually create a materialized view. So that computational power that actually joins 5 tables together is now stored in one location under a name, and it's periodically cached, and it refreshes on its own. And then all I have to do is query this view or materialized view to retrieve the information. And then this gives me access to subsets of my data without having to do the transformations each time that I need the information. Another thing that we could do here, if we compare them to materialized views, and I've kind of touched on this already, is that virtual views that provide reusable references to our data sets. And so these are good for what we're trying to do. So since they're virtual and they provide a reusable reference to a set of data, but they're not physically storing any data. Now, we can define using SQL, and we can use this as physical storage if we wanted to, but materialized views are defined using this SQL, just like a regular view. The only difference is, and I'll say this again, between a regular view and a materialized view, is that the materialized view will physically store the data which BigQuery uses to improve its performance. And the regular views, non-materialized views, they will actually not store any data, so they have to compute the table each time that you query it. So that's a slight difference between the other. So it depends on what you're doing. Do you want to trade computational power for storage or vice versa? It depends on the use case. But that's really all I have to say here about views and materialized views, and just some typical table types as well on how to actually name the tables in BigQuery. In this video, I'll discuss how functions and stored procedures can be called in the context of BigQuery routines. Let's first understand what a BigQuery routine is. So BigQuery routine are a resource type that includes stored procedures, what's known as a user-defined function, or a UDF, and these could be remote functions, and table functions. And what we're going to talk about each one of these things are these type of procedures and user-defined functions that can be used on a table or across many tables. And what we're going to do is have these routines stored in the location with a name, and then we can call them with the execute command in SQL to allow us to run those procedures or user-defined functions or table functions when necessary. So let's talk a little bit about routine execution and permissions. So to execute a routine, you have to have the BigQuery.routines.get permission on the data set. So that has to be set, and this will contain the routine itself. And permissions to access any resource has to be referenced by the routine, such as tables or views. And this is by default. You need to make sure you have those permissions in place. For UDFs and table functions, you can even authorize the function to access those resources on the actual caller's behalf, which would be your user. And what we're going to do now is create a routine, and we have a kind of a process that we have to worry about. So we have BigQuery.routines.create, which is a permission that needs to be attached to the routine. And we need to use the SQL API to assign this. And then we can run a data definition language statement using this routine. Now, depending on the routine type, I can run one of these following data definition languages. So I can have a stored procedure, which will allow me to create a procedure, create function, which allows me to create a user-defined function, or I can create a table function with the commands create table function. And these data definition language statements are what's going to be enabled when we give the BigQuery.routines.create permissions. So let's go ahead, and now I have a bunch of routines in my BigQuery instance. How do we list the routines in this data instance? So this is where we need to have the BigQuery.routines.get and BigQuery.routines.list permissions attached to this instance. So this is where I can use the Google Cloud Console. I can open the BigQuery page. I can go inside of the BigQuery Explorer, and in the Explorer panel, I can actually go underneath my project and select a data set, and then there should be a routines list there that I can actually utilize. Now, other BigQuery view operations that are useful to have, so I can actually view the body of routines. So this allows me to view what's actually in the routine, and this is something that I can have in the BigQuery.routines.get permissions. That's enabled by the console SQL BigQuery API. And I can even have an operation to delete a routine, which has its own set of permissions called BigQuery.routines.delete permissions. And this is in the Google Cloud Console. You can open that BigQuery page, and you can actually see all the routines lists. And then from there, you can actually just type delete in the dialog, and then click delete to confirm to actually just delete the routines. And it's simple as that. There's also different command line tools from BigQuery and Google Cloud that allows us to do all of these operations through the command line rather than through the console. So that's a little bit about view operations and listing routines and what routines actually are when we work with BigQuery. In this video, I'm going to describe how BigQuery connections can be used to query data outside of BigQuery. Let's first understand what these connections are. So BigQuery allows us to query our data that's stored even outside of our BigQuery in Google Cloud Services. So I can use things like cloud storage or Spanner. And these external connections will use the BigQuery connection API. I can even look into things like third-party sources like AWS or Azure. And these connections are what's going to allow us to query those information. So if I could store details about customers in Cloud SQL and data about sales in BigQuery, and I want to join the two tables in a single query, I can use this Cloud SQL connection tool to the external database by using this connection API. Now, BigQuery connections, obviously we should be worried about security. Now, connection is encrypted and it's securely stored in the BigQuery connection service. Users can be given access using BigQuery identity and access management roles, and you can grant them this kind of identity and access management so that people can utilize these connections that we have stored. Now, the connection types come from the cloud storage structured data. That's one type. These connection tables, such from Big Lake tables, for example, helps us connect the external data sources and retain fine-grained access control and security. So we've got things like structured data in our cloud storage. We have cloud storage as unstructured data as well. I can use Amazon S3 with what's known as BigQuery Omni. And there's even Azure Blob Storage access all through BigQuery Omni as well. So no matter where the data lake is stored, even if it's on another cloud provider, I can actually use BigQuery Omni to retrieve it. Now, there's other things known as federated queries that allows us to do these things. So we've got what's known as federated connections that establish connections to databases before we even send the query. So we've got things like our spanner, and we have things like our Cloud SQL. And these two things are what allows us to actually send these connections to different databases before I even send the query at all. Now, remote functions let us implement functions that are stored in any language. So we've got, I can run this in Cloud Functions or Cloud Run, for example. So a BigQuery connection will just let me connect with those Cloud Functions and then run those functions anytime I need to. And BigQuery connections will permit connections for executing these functions. It even grows a little bit further than that if we wanted to work with Apache Spark. So Apache Spark allows us to store procedures for Spark, and it lets us run these stored procedures that are written in Python using the BigQuery engine. So a Spark connection is what's going to allow us to connect to different services such as Dataproc Serverless and run the stored procedures for Apache Spark. So that's a little bit on the different tools here that are offered by BigQuery and when it comes to connection and connection security.
In this video, we're going to compare and contrast on how search and vector indexes are used to improve query performance in BigQuery. Let's go ahead and start with the idea of what a search index is for. So BigQuery search indexes just allows us to use Google SQL to find unique data elements that are buried in our unstructured text and semi-structured JSON data. So it's a way for Google SQL to quickly find the information that we need. And I like to think about it as like an index in a book. If you've never used an index in SQL, think about a book that has an index inside of it. It's usually in the back of the book. You look for terms, and if you say, you have a car manual, for example, and you look for tires, the word tires in your index, you'll find the word tires there, and it'll be some page numbers. So you know that if you go to page 87 or 38, you'll see that there's the word tires that shows up on that page. So it allows us then to go find that information on that page, to look for that kind of text. So that's what an index is used for in SQL. And so we're leveraging that power, except with JSON data and unstructured data or semi-structured data with Google SQL. And the way this works is that we're using what's known as columnar store, and it's going to search in a single spot, a single platform. So I might use this to find specific error codes in a text payload that is for identifying log files in an API, for example. If I'm interested to see, what was the average latency over the last 1,000 requests made to my API, that kind of thing. So here are some more use cases. So I get to actually search a system or network or application logs that's stored in BigQuery tables. I can identify some data elements for deletion to comply with some regulatory process, such as GDPR. There's some troubleshooting that I could support developers with by having this kind of store. And I get to perform security audits so that I get to know who's accessing what, how often are they accessing it, and should they be accessing it. I get to create some dashboards that require some highly selective search filters. And finally, I can search for pre-processed data. Now, the roles and permissions for BigQuery search, there's a few different ones that we have to make sure that are enabled on our IAM permissions in order to do this. One of them is to actually create the index, and it's called BigQuery.tables.createIndex IAM permissions. This is what's actually used to create any index in BigQuery. And there's one that's for deleting our index. And so this is BigQuery.tables.deleteIndex, and that's required to actually drop those searches. Now, these are useful, and you want to make sure that if you're going to be working with this kind of statements, like creating these indexes, you need to make sure that you have these two at least enabled to allow you to add them and remove them. And that's really it. And then from there, you can actually work with what's known as a vector index. Now, a vector index is just a data structure that's used to use what's called the vector search function
And this just allows us to perform a more efficient searching called vector searching for embeddings of our text. Now, I'm not really going to talk about the difference between here vector search. It's a specific thing, and to go underneath the hood there is kind of goes beyond the scope of what we're working with here in BigQuery, but just know that vector searching is faster. There's a bit of a trade-off, though. It reduces our recall, and it returns more approximate results. So it's faster to retrieve information, but it gives us more approximate results, whereas the just regular indexing kind of gives us more accurate results here. Now, what's actually happening in a vector index is it's using what's known as an approximate nearest neighbor, and this is just to help improve our search performance in this case. Now, again, this algorithm, I'm not going to go too deeply into that, but the key here is that this is approximate. It's much faster to retrieve information, but the results are going to be approximate. They're not going to be exact. So there's some index management options that I want to discuss. So one is that we have what's called a default shared slot pool. So to create indexes and have BigQuery maintain them, there's two options. One of them is known as a shared slot pool. When the data that I plan to index is below a certain threshold of size for my organization, I can use this free shared slot pool for index management. And BigQuery will manage this for me. It will do all of the necessary, maintenance steps for the index in the background for me, so long as it's beneath a certain threshold. Now, if I exceed that threshold, now I'm going to have to shell out some money to do this. And this is where I have to use my own reservation. Now, this allows me to achieve more predictable and consistent indexing process on a much larger production workloads, where I have my organization limit is too much data is being stored beyond my organization limit. So I have to use my own reservation. And this is where I can use my own reservation for index management. The thing is that yes, I get more predictable and consistent indexing progress on a much larger data set, but like I said, it does cost some money because now you're actually storing information that's greater than the free amount that's allotted for your BigQuery account. So just something to actually keep in mind. There are no table size limits when your indexing job runs in a reservation. That's fine. I can use my own reservation. It gives me flexibility in my index management. And I can create a very large index or make a major update to an index table. And then I can even add more slots to my own reservation so that I can have more indexing happening across a large number of tables. So that is a little bit on index management, the difference between vector indexes and regular BigQuery search indexes, and how they integrate with Google SQL. In this video, I'm going to show you how we can actually upload our data into BigQuery from a file or Google Sheet. Let's first get started with loading data into BigQuery. There's a few different ways that we can actually load our information. One of them is we get to use a batch load, which is a set of data records that we just have in a file. We can actually just store them in. And take whatever's in this file and store it inside of a BigQuery table. Another one that's useful for Internet of Things applications or IoT applications is streaming. This allows me to create individual records or batches of records. We can also use queries to generate new data and append or overwrite the results to a table. And I can even use third-party applications or services that enable a write into BigQuery tables. Now let's talk about batch loading here. Now with batch loading, I load the data into a BigQuery table in a single batch operation. It just happens once. So for example, my data source could be a CSV file or an XML file or a JSON file, or it could be an external database, or it could be a set of log files. And really what I want to do here is just utilize a extract, transform, and load job that falls into this category to open the file, maybe transform some things into the file, and then load it into a BigQuery table. Now streaming, a little more complicated, but this is where I get to continually send smaller batches of data in real time as soon as they happen. So this data is available for querying as it arrives. So I could have a storage write API, which supports high throughput streaming ingestion with exactly one delivery. I can have what's known as data flow, where I can use it with Apache Beam to set up a streaming pipeline that writes to BigQuery. I could have a data stream itself, which uses BigQuery change data capture functionality and the storage write API together to replicate data and schema updates from operational databases directly into BigQuery. I could also have a BigQuery connector for SAP that enables near real-time replication of SAP data into BigQuery. And there's one more that we can actually utilize, which is quite useful. It's called PubSub. This is a messaging queuing service, so you can use to coordinate some streaming analytics and data integration pipelines. So then whenever something is published to a topic in Google Pub Sub, it will now same event, that topic, to a BigQuery table. And so I can use BigQuery subscriptions to write messages directly into that existing BigQuery table. Now here's how we can actually generate our data. We can use SQL to generate data and store these results in BigQuery with what's known as a data manipulation language. Now, these statements perform bulk inserts into an existing table, or they store query results in a brand new table. But the idea is that I'm writing some SQL to either create a table and then insert data, or just insert data into an existing table. Speaking of creating tables, I get to actually use a create table as statement to create a new table from a query result, which is perfectly fine to do as well. And I get to execute queries and save them to a table. So when I append the results to an existing table or write to a new table, this is what we're actually doing. I'm writing my query results to a system, to a table that already exists. Now, third-party applications and services provide connectors that can ingest data into BigQuery. Not all of them do, but some of them do. And these depend on the tool that we're actually using. But for example, if we wanted to load data from external sources to BigQuery's storage, I can use what's known as an Informatica data loader or Fivetran data pipelines. There's many different third-party applications that will connect to, say, a CRM and send that information into BigQuery for us to analyze later. Now let's see here. When we talk about considerations for selecting a data ingestion method, what exactly are we referring to? Well, the first thing we want to look at is to our data source. So the source of data, or the data format, can determine whether I use batch loading or streaming is simpler to implement and maintain. So if I'm always thinking about the data transfer service and how it supports the data source, and if I can transfer the data directly into BigQuery, it might be the simplest solution to implement, or it might have some third-party sources that aren't supported by the BigQuery data transfer service, so I have to transform the data into a format with batch loading. So there's many different ways that we have to look at it, but it depends on exactly what our data source is. So if you go to the data source, whether that's a CRM or your application logs or whatever they might be, you have to start there and figure out, okay, if I have flat files, I can use batch loading. If it's like an Internet of Things application, an IoT application, I can use streaming. Well, that's where you start typically. Now, there's also slow changing versus fast changing data. So imagine if I need to ingest and analyze data in near real time, I might have to consider streaming the data, such as an IoT application. Now, with streaming, the data is available for querying as soon as the record arrives into BigQuery. We want to avoid using data manipulation language statements to submit large numbers of individual row updates or insertions. So for frequently updated data, I use streaming so that we have a change log and use a view to obtain the latest results. Now, when it comes to Cloud SQL, what we're doing here is using an online transaction processing database, and we want to use federated queries to join the data into BigQuery. Now, this is slow changing data. This is where I can actually get away with using batch jobs. I'd use a simple load job. So if my data needs to run daily or hourly, I can load those jobs in less expensive computational resources, and it just uses fewer system resources, so it saves me some money. But if I'm dealing with an Internet of Things application that's fast changing data, I need the records as soon as possible, then I'm going to have to use like a change data capture or some type of streaming to get that information into the system. Now, reliability is important. So BigQuery has a service level agreement, but you need to consider the reliability of our solutions that we're going to be implementing. So if you have loosely typed formats such as JSON or CSV, bad data can make an entire load job fail. So I need to make sure that I have proper data cleansing before loading, and I need to consider how to respond to those errors as they show up. So I also encourage people to use a strongly typed format, such as a Parquet file, because you can actually have some type of type checking in there to make sure that, okay, I'm expecting a string, I shouldn't get an integer, or I shouldn't get nulls, or I shouldn't get something. It just allows me to validate the file before I even start transforming it or loading it into the system. Latency is a big resource here. It's something you should take into account. How much data you load and how soon you need the data to be available is really important. With streaming, it offers the lowest latency of data available for analysis, but it's also the most expensive to do. Periodic load jobs have a higher latency, but they're cheaper. So new data is only available after each load job finishes, but you do save some money on that. So it depends on how quick you need the data for your business use case. Another thing that I'd also talk about is the data ingestion format. Now, I have to start with a base format. So schema support, if I have a Parquet file, they can be queried. So BigQuery can create these table schemas automatically based on the source data. But if I'm dealing with JSON and CSV data, I have to provide an explicit schema. Or I can use what's called a schema auto detection, but still you should have some type of type checking to make sure that the types actually match what you're expecting. So flat data or nested data in repeated fields, like you see in JSON, for example, and Parquet files, they all support flat data. And what I want to make sure is that when I'm dealing with nested and repeated data, I know it's useful for expressing hierarchical data, but I also need to reduce the data duplication when loading the data into the database in order to save some space. So these are just some of the things that you want to look at when it comes to data ingestion. Exactly what's in these files, what format are they in, are there repeated information, how are you going to create these ETLs so that you get to remove those repeated information so that you're not wasting resources on storing information that's duplicated. So that's a little bit on the Google BigQuery and some of the considerations for selecting a data ingestion method. In this video, we're going to describe the various options to load our data, including SQL and using the BigQuery data transfer service. Let's first start with the idea of batch loading. And when we run batch loading operations, there's a few different ways that we can actually run them. What we're doing here is we're trying to load our source data into a BigQuery table in this single batch operation. And this is where we can use traditional extract, transform, and load jobs to load files that could be CSVs or information coming from an external database, or it could be a set of log files that we have generated. Now, when we run BigQuery operations, we can run them either as a one-off. So those simple transfers could be done once. I can use an orchestration service such as Cloud Composer to schedule and load my jobs, or I can use a cron job to load data on a schedule. Or I could just use the BigQuery transfer service to actually just do this one time. Now there's some options for batch loading in BigQuery that will allow us to do certain things such as loading our jobs or retrieving information using SQL from another database, or there's other managed services, but they all primarily fall into one of these categories, either one-off or on a schedule. Now, load jobs load data from cloud storage, or they are a local file by creating this thing called a load job. Now, the records can be in any format, such as Avro, CSV, JSON, ORC, or even a Parquet file. But they are from a local file that's stored in cloud storage, and we're going to load that information that's already stored in the cloud into a SQL table, in a BigQuery SQL table. Now, SQL means that we're going to use the load data statement. So this means that we're going to either create a new table or use an existing table, and it's going to load data from one or more files into that table, and then we can use a load data statement to load CSV files, JSON, Avro, ORC, or Parquet files. Now, the BigQuery data transfer service is a service that automates data movement into BigQuery, either on a scheduled or managed basis. And the analytics team is useful for this because they can lay the foundation for BigQuery data warehouse without writing a single line of code. So this is a Google Software as a Service, or SaaS, or third-party apps and services. Those are all supported sources for the BigQuery data transfer service. And the great thing is that it's very low code. So when all you have to do is configure a data transfer, and the BigQuery data transfer service will automatically load our data into BigQuery on a regular basis, or as a one-off if you choose to not need it on a scheduled basis. We also have the BigQuery Storage Write API. Now, this is just a unified data ingestion API for BigQuery. It combines streaming ingestion and batch loading into this high-performance API. And what we're doing here is we're just trying to batch process a large number of records. And so this means that we're going to get exactly one delivery semantics. So the Storage Write API will get exactly one write through the use of many streams. So this means you're not going to see a lot of duplicated data coming from this. So we receive a message or an event, and it will write to the BigQuery. You're not going to see it multiple times. And we can commit records in a single operation. So that's useful for this. So when we are dealing with this kind of operation, we're collecting as many records as we can that we want to write to the database, and then we are actually going to commit. And we're going to see all of those records show up in the database table, or none of them will show up. And that's the idea of having a commit. There's some other managed services that we can use where we can export our data from external data store. So you might want to use, for example, a Firestore export. So when choosing a batch load method, most file-based patterns should either use a load job or a load data SQL statement to batch load our data, or you could actually just use the import statement into BigQuery, and then that will retrieve your information. So all you have to do is then export your data from Google Services, and then that's going to give you a file, and then there's an actual import button inside of the BigQuery console that you'll be able just to take that file and load it into a table that way. That's one way to do it if you're looking for something manual and just one-off that you need to do. But another thing you can do is you can actually just export thing from the external data store yourself and give them over to a Google Data Transfer Service, and then that will also do it on a schedule for you. So there's multiple ways to actually tackle this. Some of them require other services by Google Cloud, but another way you can also do it the old-fashioned way, the brute force way, I like to call it, by just grabbing the file that you need from your source, importing it into the BigQuery console, and then actually going through the steps to create your columns and your tables or update an existing table. And that is how we can transfer our data from several different sources using SQL, load jobs, or the BigQuery Storage Write API. In this video, I'm going to describe the steps that would be taken so that we can allow for controlled user access to data sets. So let's get started with understanding what it means to authorize a data set. Authorizing our data set involves describing how we want the data set to be accessed and by who can access this information. So we can authorize all views in a specified data set to access a second data set, which is perfectly fine to do that. So it's a way for me to authorize the views inside of my data, and then with an authorized data set, I don't even need to configure individual authorized views because I have a full window to the data set provided to the user. And so now I can create an authorized data set in BigQuery by either logging through the Google Cloud Console or using the BigQuery command line tool, or I can just call the API directly with datasets.update and actually just make it into an authorized view. Now, when we control access, we're controlling access with the Identity Access Manager, or IAM. So what this means is that I want to be able to view the access policy that's associated with the data set in the IAM role, and I get to grant access to a resource all within the Identity Access Manager, and I can even revoke access to a specific resource, and it's all done through this manager. Now, there are some required roles that we have to give in the Identity Access Manager. So we need to provide the BigQuery Data Owner role. So if I'm trying to modify these policies for resources, I have to ask the administrator to provide me this Data Owner role. And this is where I am now associated as a data owner in BigQuery, and this is where I can contain permissions for modifying the Identity Access Management policies for specified data sets. Now, tagging tables and data sets is another way to actually organize our data and sort of provide granular access to certain windows of our data set. So I can assign IAM policies to BigQuery tables and data sets as a part of a group. And this means that I can apply conditions based on whether a resource has a specific tag. For example, if I have many different tables dealing with different entities in my BigQuery platform here. So what that means is that I could have a customer data set So there are a few tables that are associated with customers. I could have one that is for retailers if it's some type of retail application. So basically, now I have tags associated for customers or retailers. And if I want to provide access to those tables that are associated with customers, I can now just, instead of individually specifying the table names, I can just specify the tags that are associated with those tables. So it's just a way for me to organize my information a little easier. Now, there's also VPC service controls for BigQuery. This allows us to restrict access and exfiltration. So these VPC is like our virtual private cloud, and this is where we can set them up, control, and monitor inside who has access to our VPC. And this is where I can actually restrict access and exfiltration. Anybody who tries to break into my system, I'll be able to see who's trying to get in. And it can be created and managed just like any other VPC service controls that we've used before in Google Cloud. So things like BigQuery Omni VPC service controls or Analytics Hubs VPC service controls, those are all done the same way. Not only do I want to share data sets with people within my organization, there are times where I want to share a data set with the public. So I can share any of my data sets with the public by changing the data set's access control to allow access by, and it's literally in quotations, it's called all authenticated users. And so this means that anybody who has a Google account will be able to access this information. Now, when you share a data set with the public, obviously make sure that you're supposed to be sharing it with the public, but make sure that you understand that the storage charges are incurred by the billing account that's attached to the project that contains the publicly shared data set. And you're going to be charged for queries that are incurred by the billing account attached to the project where the query jobs are run. So that's really important in terms of understanding your billing. If it's expensive to make a data set visible to the public, but there are cases where you will need to do that, and this is how you can do so, is just by allowing access for all authenticated users, meaning that anybody who has a Google account, and just keep an eye on your billing cycles so that you know what you're paying for. That's a little bit about sharing data sets within an organization and outside an organization, as well as some VPC service controls. In this video, we're going to discuss some pricing models and optimizing some of our BigQuery costs. So we're going to select between different editions and pricing models inside of BigQuery, just so we can maximize our cost efficiency and for various business needs. So we'll talk a little bit about them. Let's start with the idea of what BigQuery pricing is based on. So BigQuery is just a serverless data analytics platform. So we don't need to actually provision any individual instances or virtual machines. It's all serverless. And instead, what BigQuery is actually doing is it's allocating computing resources in the cloud as we need them on demand basis. So if I run a very complicated query, it might take more resources than a simple query. And so those two queries will cost a certain amount. Obviously, the one that is very complicated, that uses more computational resources, will cost a little more than the one that's simpler. So these slots can be reserved in advance. So if I can reserve compute capacity ahead of time in the form of slots that I can just ahead of time say, you know, I'm going to be running these size queries. They're going to use a certain number of virtual CPUs. And that means I'll need like maybe 3 slots. If let's say each slot has 2 CPUs in it, so I'll need 6 CPUs. Now that is going to reflect the design of BigQuery, right? So I'm paying for the slots that are allotted for my BigQuery instance, and then the queries can then go ahead and use some of the computational resources from each slot. What you'll notice here with BigQuery pricing is that the projects you create, they'll all have a billing attached to it, like a billing account. And so what we're going to do here is BigQuery is going to charge for other operations, not just queries. So if I'm trying to run a BigQuery job in the projects that are billed to the attached billing account, that's where I'm going to get billed. It's not just running the queries that I have to worry about, it's also storing them, storing the results. So these costs and trends will have like a free operations and a free usage tiers just to sort of start things off. So there's a free storage tier, a free computational tier. So if I need a certain number of CPUs, a certain amount of storage, and they fall within the free package, then I don't have to pay for BigQuery. I can just go ahead and use that. But as I use more storage, as I use more CPUs, that is where I'm going to start getting some charges. And the other operations could include things like BigQuery Omni, BigQuery Machine Learning, and just streaming reads and writes. But BigQuery also has this free operations and a free usage tier that we can also leverage here. Now, BigQuery pricing components involves obviously the compute pricing. This is the one that is going to process our queries. So how much does it cost to actually run our SQL queries, our user-defined functions, our scripts, really any type of data manipulation language and data definition language statements that we create on the engine. That's going to require a certain amount of computational time with a certain number of computational resources. And so those two things are what's going to factor the price of that operation. But it's also not just computing information, it's also storing the information. And obviously, this is the cost to store our data and that I load into BigQuery. Obviously, the more data I store, the more it's going to cost. Now, BigQuery has a few different pricing models. One of them is known as the on-demand pricing. This is where I'm charged for the number of bytes that I'm processing for each query. So the first 1 terabyte of query data that's processed per month is free. After that, I start paying for the amount of queries that I want to use. Now, the interesting thing is 1 terabyte of data is a lot. So if you're like a small company, you could actually leverage this on-demand pricing pretty easily. Now, the capacity pricing is a little bit different. Instead of paying on the per terabyte store, where the first terabyte is free, we are now paying on a per slot hour. So remember, a slot is just a number of virtual CPUs that are associated with actually running the queries. So if I'm using 1 slot for a certain number of hours, I'm going to get a certain price from that, right? So this pricing model, I'm charged for the compute capacity that's used to run the queries, which is the virtual CPUs, over time. Now, I can use the BigQuery autoscaler or purchase slot commitments ahead of time. And these are dedicated capacities that are always available for our workloads at a lower price if I choose to, or I can just use the autoscaler. The autoscaler is just like a way so that BigQuery engine says, okay, this is a very complicated task. I'm going to need 3 slots to do this. This is a less complicated task. I'm going to need maybe 1 slot to do it. So depending on the complicated query that I'm pricing, I get to pay on a per slot hour if I choose to. Now, the storage pricing, like I was saying, it is the cost to store our data, and you're paying actually for one of 2 things. You're paying for the active storage, which includes any table partition that's ever been modified in the last 90 days. That's active storage, okay? So it's things that have accessed or modified in the last 90 days is called active storage. Another thing that you're paying for is called long-term storage. This is any table or partition that hasn't been modified for 90 consecutive days. And this is the important part. So the price of our storage for that table will automatically drop by approximately 50% because it's treated as an archive. It's something that is stored for a very long time. Now, there is no difference in performance between active storage and long-term storage, or durability or availability between the active and long-term storage. This is just a way for us, there's less work that needs to be done actively by this serverless engine, so it archives it for us, and it keeps things a little bit easier for us to handle. Now, there are other BigQuery pricing considerations, and I'm not going to discuss all of them here, but just so you have them for completeness, you know what they are. This is the data transfer service pricing if we're moving information from one location to the other. We have BigQuery Omni pricing, data ingestion pricing. We have data extraction pricing, data replication pricing. There's also some external services that we can use that also have a different amount of pricing associated with that. So if we're trying to link it to Amazon S3 or some other third-party cloud provider. We have obviously the BigQuery machine learning pricing as well. And we also have the business intelligence engine pricing, as well as some free operations or free usage tier and flat rate pricing. So these are just all the different pricing models that are available here with BigQuery. And that's just, we're just scratching the surface here. So depending on what we're trying to do, what operations we're trying to handle, what usage tier we're on, we all could pay a completely different price. And so it's something to keep in mind when you're trying to design a solution with BigQuery to solve a problem for your organization. In this video, I'm going to describe the use cases for using Looker to visualize data from BigQuery. So Looker is a visualization tool, and it's used to explore and share our data. Now imagine if you want to
explore your data in BigQuery. This is where we can use it. We can also share our data with other members in our organization. And importantly, we can actually create visualizations and dashboards that can help us make better business decisions. These are the three kind of purposes why we use Looker, especially when it goes hand in hand with BigQuery. And so we can get this customized data experience, and we can have these data applications, and they're all embedded analytics that goes beyond just a simple dashboard in applications. So I can transform my data in this value-driving system. So I have this fully interactive dashboard. It can be integrated in other applications, not just with what I'm looking at. I have an API that allows me to do just about anything from the UI all through an API call. So I have this unified trusted source for AI and human analysis. So I can actually give some type of analytics with artificial intelligence. In fact, it's powered by Gemini for self-service business intelligence. And this is where we can get this self-service analytics, where I can actually go ahead and see if I can answer some questions about, what was the sales cycle like, the average time to close for my business deals from the last quarter and the last year, and try and see how does this make a difference. And this is where I can get this self-service business intelligence from through the self-service analytics, and powered by Gemini to sort of analyze my data in the dashboard and give me some context to what I'm looking at. Now, Looker Studio is a business intelligence tool that is practically just there to help us make better business decisions. And here's how it works. You can create and share reports and data visualizations. I can connect it to about 800 different data sources, including ones from BigQuery. I can also create what's known as smart reports, where I can power them with a artificial intelligence tool, such as Gemini. So I can create this impactful business metrics and KPIs, and had some dimensions with intuitive smart reports powered by artificial intelligence. I can share automated dashboards as well, and I can also create meaningful, shareable, and customizable charts and graphs with just a few clicks. It's all very low code. Now, here are some more key features of Looker Studio. It offers an easy-to-use web interface, and so you can actually just drag and drop your objects. It's simple as that. You don't actually have to write any code at all if you don't want to. There's also report templates that are available, so you can actually use a report template to visualize our data in just minutes, so it's very quick to get business intelligence from. All I have to do is just connect my data sources and customize the design to meet the needs that I'm looking for. I can also have data connections, such as pipes, to connect Looker Studio to underlying data. I also have the Looker Studio API, where I can actually make some API calls through the G-Cloud command line interface, or I can use them with the API directly. And what's fascinating is that not only can I generate the reports in the web interface, but there's a way that I can actually take that report and embed it in other web applications, either via HTML. And so that's what I can use there. And there are some benefits to using Looker Studio. One of them we've already talked about. It's how powerful and simple to use it is. It's very simple to get started. It's all done through the console if you'd like, or you can use the command line interface with its API. You can connect a huge variety of data sources, not just BigQuery, but many different other third-party tools as well. And you can share and collaborate in real time with other people within your organization. And so this is where we can take our reports that created, and we can share them with the public or people within a team, and we can embed those reports in the web to our web applications if we so choose to. And that is a little bit on the advantages of Looker Studio. In this video, I'm going to show you how we can actually create a Looker Studio dashboard, and it's quite simple on how to get started. So let's go ahead and go to the lookerstudio.google.com webpage. You'll be met with a page that looks like this after it asks you to sign up and authorize your project to use Looker Studio if you haven't done so already. But finally, you'll get to a page that looks like this. It's a list of all of our reports. You can see that there's some sample reports that are already created for our template gallery for us. What we're going to do is just go to our top left and click Create. Now this little window will pop up, and we're just going to go ahead and click a report. So now this report has been created. It's going to ask us to add data to our report. Now I'm going to be querying BigQuery, So I'm just going to scroll down just a little bit and query some BigQuery. And we're going to go ahead and scroll to the left here. And we're going to be seeing that there's our project that I have created. Your project might be called something different. But what I'm going to do is actually use a custom query to actually query a public data set. So first I'm going to select custom query, and then I'm going to select the project that's attached to that custom query. Now I have some SQL that's already written to filter this data from a public data set that's for United States names per year. So it lets me know what's the most popular names in different states. For example, I'm just writing a simple SQL command here to retrieve the name and then group by the name, and then filter that public data set, this USA underscore names dot USA underscore 1910 underscore current data set by the state of California in the year 2000. And I'm just going to group it by name and then order by total number of descending. Now that's cool. I'm going to go ahead and click add. And this little thing should pop up now. It's just telling me that I'm about to add data to this report, and that's good, and I'm going to go ahead and be happy with it. Click add to report. Now this data should show up, and you'll notice that there's already a table that's created for us. There's 3 sections to this Looker thing here, this Looker dashboard that you're seeing. First section is kind of our canvas where we're going to actually create tables or charts, things that we're trying to communicate. It's going to go here. And then in the middle section is the chart page where we can actually change the template of what the chart will look like. Now by default, it already creates a table for us. So it's there. And then here's where we can actually change everything, including the style and what the dependent variable looks like. So what I'm going to do now is actually, instead of using the record count, that's why the record counts don't really make a lot of sense for us right now, I'm going to select record count underneath the metric and change this to the total number. Now, this makes a little bit more sense to us. You can see that it says Daniel. It tells us the total number is data for 4,357 babies were named Daniel in the year 2000 in the state of California. That's the most popular name, and so that's useful for us. What I want to do now is go ahead and see if I can change this metric into a bar graph. So how can we do that? Well, let's say I want to keep this table. I'm going to go up here to where it says add a chart, and I'm going to come down. You can see that there's a canvas here. There's a few different options for me to choose. So I'm going to go ahead and click bar, this column chart right here. And now you notice how my cursor just turned into a bit of a crosshair. It tells me where I want it to go. So I'm going to place it right here, and it's going to create a default view of our data for our chart. It's not a problem. We can resize it by hovering our mouse over, just like we would in a Google Doc. And I can just move it over and align it in any way I see fit. So what I want to do now is just change what's happening here on the chart. I can actually change the style. I can make it into a horizontal bar chart like so by clicking style. Or I can have it vertical. I can change the number of bar charts. Maybe I don't want to show 10 bars. Maybe I only want the top 5. So I can scroll it down to 5 and just give it a moment. And now you can see the top 5 names, which you can see is Daniel, Anthony, Jose, and Andrew from the table above. So that looks good. That's perfectly fine. So now I can actually have it colored in a different setting. Maybe I can click color, and I can change the style to maybe green if I choose to. And this just makes things a little bit easier for me. And now I can actually, if I want to, I can actually share this dashboard with someone else by going up to the top, clicking share, and actually entering someone's Google account so they can actually see the data. And this is going to be live data. So right now this is a static data set. It's not really changing. But if, as you can tell, I'm streaming data into this table, into this data set, for example, I'm not, because this is a public data set, the changes will be live. So as updates are showing up in BigQuery, you can actually see how they're performing live in front of you on this dashboard. And that is a little bit on how we can actually create a report inside of Looker Studio with Google Cloud. In this video, we're going to talk about how we can share reports from Looker, and identify some of the methods of sharing Looker reports for ensuring that there's safe access that can be granted to other Looker reporters.
So let's understand what sharing Looker data means. So we know that Looker is just a way for us to actually create these dashboards. And there's a few different methodologies to take that data in the dashboard and share it from everyone or with a select group of people. We can share data. Public sharing, importing, and embedding of looks is what they're called. So this gives us public access to data using URLs, embedding, or placement in spreadsheets if we choose to have them. It allows us also to share data through an Action Hub servers to deliver content to third-party services that's integrated within Looker. We can also have downloadable content, so you can actually download our data or visualizations from looks and explorers and format those downloads to our application that we're trying to integrate it with. We can also schedule our deliveries to Slack integration, which is quite useful. So I've seen this happen where we can have a Slack channel, and so that Slack channel is just meant for Looker to place graphs and data in that Slack channel, and you can have it set every week on a Friday to deliver that kind of graph and data, that kind of insight, so that people can see it there. And so it's just a way for us to actually show a report, and having it in a Slack channel is convenient for some organizations. And we can also share data from our URLs. So I can share data using a browser, short or expanded URLs if I choose to. And this is just a standard HTTP URL, so we can just use any browser at all to retrieve it. And I can actually deliver content using what's known as the Looker scheduler. Okay, so those are some of the methodologies here. Let's dig into one of them here. This is called sharing data from our URLs. So from within Looker, I can grab any one of a series of URLs and then make them available to users or users outside of our Looker instance, and they can open a query to actually see what's going on in them. So other users can open a query or what's known as a look, and then this is going to send data from Looker to other destinations outside of our Looker, and this is just publishing a look within a public URL. So I'm sharing this URL using a number of methods. This is actually quite useful for this. So I can use a short URL, an expanded URL. There's all sorts of different formats of URLs that I can use. And that's pretty much it. No different than actually sharing a Google Doc, really. It's quite simple for that. Okay, so let's look at downloading content. So how do we do that? So to download content, you must be given the download with limit or download without limit permission in your Identity Access Manager. And this is going to be done by the Looker administrator. And then you can download from a look or explore or a dashboard or some type of a merged results query. And then I can download them in certain formats such as text files, Excel spreadsheets, CSV, JSON, even HTML, Markdown, and PNG images are all available for this. So then I can just pull down that format and I can use it in whatever context I'd like to. And that's the easiest way to handle this downloadable content. Again, very similar to any other file management software that we've used, even Google Docs. Now there's public sharing, importing, and embedding looks. So public sharing URL setting must be enabled. Basically, it says that for a specific look, I can make this publicly accessible. And so this means I just take those URLs and it'll provide a list of shortened or unguessable public URLs. And those URLs allow anyone that you share them with to view the data or its visualization that's attached to that URL. I can enable public access on the look you want to share. So that's very important. Otherwise, this URL will not be publicly accessible. And that's pretty much all we have to do. And it's all done through the settings window to allow us to share this information. Is one way to handle this. So I can deliver documentation for Looker admins one time on a certain day, or I can have them set up to be a recurring content delivery. So, recurring content deliveries or schedules to one of Looker's native delivery destinations or to a third-party service is all enabled through Looker. And this just means exactly what it is. Every month on the first of the month, I'm going to receive this look or some type of information. And I can have this include email, webhook, Amazon S3 bucket, or even an SFTP server. And so this is where I can actually just set them up to trigger something, such as sending out an email with a report inside of it. That's one way to handle it. Or I can set it up for one-time content deliveries. So for an ad hoc delivery of a look, I can send it over to an email or an SFTP server or an S3 bucket, whatever really I'm looking for. I can also schedule these deliveries to a Slack integration. So this allows me to install what's known as a Looker app in the Slack workspace that I'm going to be receiving the messages in. And then I can configure my application settings in the Slack workspace to connect to my Looker instance on my Google Cloud account. And then from there, all I have to do is just get Looker to send it to that particular channel. And this involves me getting a Slack API token to integrate inside with Looker, and so that they can communicate with each other. And that's pretty much how that would work. It's no different than sending out an email, except now we're actually just sending it to a channel inside of a Slack workspace. And that can really be done after you've authenticated with your Slack channel inside of Looker. Another thing that we can do is we can share our data through an action hub. So we can use our actions, also known as integrations. There's a few different integration or actions that are available through the Looker Action Hub. I can build and publish even a custom action so others can use it for public use, or I can build and publish a custom action to a private action hub for private use. Now, an action is just a series of tasks that need to be done with certain third-party tools, and I can have them done in sequence and then publish them to a private action hub server. And then I can just enable them so that every time at a certain time, we're going to run these series of this action here, which is just a series of tasks with third-party tools to actually deliver the content to someone else. And this is really all we're doing here. They're kind of like macros in a way to actually say, okay, I want to send an email to these people. I'd like to also send it to a Slack channel as well, so I can have these custom actions in one go, do these 5 things. When a data set needs to be shared. And that's just one way to handle it. And that is a little bit on how we can actually share data, the many different ways we can share data with Looker. In this video, I'm going to describe some of the options that are going to affect the cost of using Google Looker service. So let's understand the Looker pricing model and how this works. The Looker pricing model has 2 main components. The first one is known as platform pricing. This is just the cost to run a Looker, or what's also known as a Google Cloud Core instance, and includes platform administration, things like integration and semantic modeling capabilities. That's one of them. The other component is our user pricing. And this is just a cost for licensing individual users. We can also use them to access the Looker platform. And the costs, you'll notice, are going to vary based on the type of users they are and what their permissions within the Looker platform are. Now, Looker billing is really important because every Looker instance that we have creates a billing account attached to it. So all my charges about creating a new instance or adding users or modifying the users or doing any action at all is going to be billed to the billing account that's attached to my Looker instance. And so there's 3 different platform editions that I want to discuss. First one is known as the Standard Edition. Now, this just means that it's a product for small organizations with teams that are fewer than 50. Think of like a startup. And this includes 1 production instance. You'll also have like 10 standard users, 2 developer users, a few different upgrades. You'll get like 1,000 query-based API calls per month and up to 1,000 administrative API calls per month. This is a great starter tool if you're just using it to start visualizing data and it's not really central to your product and you're just looking for it for within internal use. Now, if you're not a startup, you're more of an enterprise location, this is where we'll have the Enterprise Platform Edition. Now, this is a product that has enhanced security features and it has a wide variety of internal business intelligence and analytical use case, and it'll include a lot of different, include a production instance, 10 standard users, 2 developer users. You can have upgrades up to 100,000 query-based API calls per month and 10,000 administrative API calls per month. So a lot more than the standard model. Now, when we deal with the embedding platform edition, it's the same kind of deal, but this is meant for people who are trying to deploy and maintain these looks or these visualizations to custom applications at scale. So think about if you are creating a dashboard application for many different clients. This is where you're going to use the Embed Platform Edition.
Now, this is where, again, you're going to have one production instance, 10 standard users, 2 developer users, a few different upgrades. The difference here is that you're going to get up to 500,000 query-based API calls per month and up to 100,000 administrative API calls per month. So that's clearly meant for an application that's meant to be widespread over a region. Now, here's a table that sort of shows you what is included in each platform edition here that we have. So you can take a moment to pause the video and actually look at what these numbers are. You can see very clearly here that for the standard, you get 1,000 API calls per month, which are query-based, or 100,000 or up to 500,000. Obviously, the one with the embed is the most expensive and standard is the cheapest one. So you'll have to take a look at which one will better suit your needs and for what purpose. Now, here are some ideas of the different types of users. Now, you notice that on the previous slide, I talked about different types of users, such as developer users, standard users. So let me just go into a little detail here of what this means. We'll have the first thing is called the developer user. This is just an end user that's provisioned on a Looker instance. And this is somebody who has access to any combination of our interface within Looker, including things like our Looker machine learning models, folders, boards, dashboards, even administration, really just about anything that can be done. So this is where we would write our SQL code, explore our data, or schedule some type of process that needs to be done over and over again. And this is all done here by the developer user. Now, the standard user is another type of end user, and this is where they only have access to things like our folders, our boards, and our dashboards, or our looks, which are what we call our individual reports and our charts. And this is where they could also run our code. And so this is just a standard user who's just meant to visualize and explore our data sets. And the viewer user is just meant for somebody who has access to folders, boards, and dashboards. They don't actually do any type of operations on our data. They're just meant to actually view the data set that's actually there. So each plan will come with a certain number of developer users, or standard user, or a viewer user. And that is going to be allotted to anyone within your team. Now, you can actually increase the number of developer, standard, and viewer users individually for your needs, but you'll have to communicate with the administrator for your Google Cloud account to be able to increase those numbers for your use case. That's a little bit about the pricing model for Looker and how the billing system works for different types of users and platform editions in Looker. In this video, we're going to identify some of the common issues that can arise when we're trying to troubleshoot with BigQuery. So we're working with BigQuery, we get some error messages. What do? So first, we need to understand the responses that are coming from the BigQuery APIs. So, when we're talking about an API, we're talking about an HTTP error code that's returned when we do some type of operation. And so this is where we'll get exactly what you might expect from a regular API, not just BigQuery. It'll return some type of error code, either a permissions error or something went wrong or a bad request. You get that error code, so it could be like 403, 404, that kind of thing. So those error codes that come from the API are a first little hint about what's coming to us. And you can actually look up these error codes and you can see their error objects in the response. And they'll not only just tell you what the status code is, but they'll actually tell you exactly what's wrong, what happened. And this is done through something called an error object, which is just a JSON body that's returned to us that contains information about the specific error that has occurred. And we want to be able to understand these error objects because the error objects will contain an array of error proto objects. And so these objects are what's actually going to tell us what's wrong here. So there could be more than one thing that could have been wrong. So report codes in the 500 range, for example, indicate a server-side error. So if I receive a 500 range response code, this is where we can start to signify what might have happened. So there could be some response body that comes with that. And so this error object that contains an array of error proto objects, those are the things that are useful for us when it comes to debug them because they're going to actually tell us what happened specific. But we'll also have an error results objects, which also contain a single error proto object. Now, the error message column in a table map to the reason a property in an error proto object has occurred. So you can actually look up what this table is on the Google Cloud documentation page, and you can actually see how to read those error proto objects because there's actually a way to do this. So you'll have like a few HTTP errors or some networking errors, and then you can map them to what the error response body will look like. Now, authentication errors is another significant portion here. So errors that are thrown by an OAuth exception returns a JSON object, and this is defined by an error key and then a description string, usually telling you that you're unauthenticated or something's not correct with your auth. But you can also see that there's an accompanied error with HTTP 400, which is a bad request, or a 401 unauthorized error with a description string. And so one of the error codes that could come back from an OAuth 2 specification could have an error and letting you know that there's an invalid client. And that lets you know that you are unauthorized or there's a bad request or something like that. Now, the troubleshooting common connectivity errors is pretty straightforward. It can be a little bit tricky depending on how you have your BigQuery instance set up. But here's just the basics of understanding this. Is you want to implement a retry mechanism and you want to set a larger timeout value so that, if something is to give you some type of connectivity issue, so it's taking longer to connect for whatever reason, this is most likely means that you have to have a timeout value that's increased. So if your timeout value is 5 seconds, but it's taking longer than 5 seconds to connect to the instance, increase that timeout value just to see what's going to happen. But also what I would do is I would implement a retry mechanism so that if something were to go wrong, try it again, and have an increased timeout value will help you with that. So you can also set a larger timeout value is really important, like I've discussed, but you can also increase the timeout value on the client side, which is useful for this. So in your client, which could be a programming language, some type of SDK, you can let it know that the timeout value for the client itself is going to be much larger. So you could set it to, say, something like 50 seconds on the client and on the server side. And that's going to help you with some common connectivity errors. These are the most common ones that have happened. Now, there's troubleshooting Google Cloud Console errors that comes with this, which is usually comes down to switching the browser to incognito or private mode and retrying. That's usually what I've done. Anytime that's happened, it's because my browser has gotten confused with some cookies or some type of settings that have been enabled in the profile I'm using in Google Chrome, for example. So I'll switch to incognito mode and then retry the process all over again. Another thing that could be potentially interfering with the console itself is your browser plugins. Take a look at what browser plugins you have loaded. For example, if there's a plugin that's kind of disabling some type of JavaScript or disabling some type of something on your system, try and remove those. I know that ad blockers have interfered with some stuff on my Google Cloud Console error before, so turning that off on Google Cloud is useful. And then obviously there's common types of errors that aren't just for BigQuery, or it's just for about any API service that you use in the cloud, is make sure that you have the proper permissions for it. So if you're getting an access denied to a project, it means that the user doesn't have a BigQuery jobs create permissions or whatever it might need, whatever operation you're trying to do. So contact your administrator to make sure that you have the proper permission set. Another common issue is that you could have your query is going to exceed its CPU resources. So you'll have an error string that says query exceeded resource limits. This is just a bottleneck that's done on all of our queries, especially on-demand queries that's using too much CPU relative to the amount of data scanned. And that just means that you need to further optimize your query. It really shouldn't be using that much. It's very hard to retrieve this, but depending on who wrote the code, it could mean that you have to refactor. And there's also some quota and limit errors that could come back. So again, for these kind of systems is that BigQuery has various limits that limit the rate and volume of our different requests and operations. And these are just there to protect the actual infrastructure, but to also help guard against some type of unexpected customer usage that could potentially spike your bill. And so this is there to let you know what that would look like. And so you'll get a HTTP 403, which means forbidden status code when you try to run an operation. And it'll give you some type of message that says quota exceeded, so you know exactly what the message is, and it might tell you specifically what quota is broken there. So that is a little bit about some Google Cloud BigQuery error codes that you might see, as well as just how to troubleshoot those error codes. In this video, we're going to identify some common issues that can arise when we're actually working with Looker and how we can actually troubleshoot these things. So troubleshooting when it comes to Looker, if you're experiencing any type of issue with a chart, report, or a data source, there are some steps that we need to take to resolve them.
One of the ones that I've noticed is very useful is basic hygiene. So, if you have some type of temporary network errors or backend glitches, you might mean that you have some type of unresponsive page. There could be a system error, or the actual Looker Studio system is just not available. So I'd start with understanding if you have proper access issues. So make sure that your identity, your authorized user, is authorized by the administrator to actually do some operations on Looker. And so that's typically what I do. So the access is important, but as well as just making sure that you don't have any unresponsive pages on your system that could be potentially blocking another page from loading. Another thing I've seen is our connections issues. So data connection issues can occur for several reasons. It's really hard to pinpoint when it comes to the cloud. But you could have, for example, a missing data source. You could have some data set configuration error, or there's no access to the actual data. This really comes down to just about anything. I've seen it also happen with database connection strings, so that could also be an issue. So make sure if your Looker instance is connected to a database directly, make sure that your database connection system is correct. Another thing I've seen is chart configuration issues. So some possible errors or symptoms could come down from the actual system error. You could have a chart configuration that isn't properly set, or you could have some type of invalid combination of metrics and dimensions that just doesn't make sense for the graph that you're showing. And so make sure that you're selecting the right fields for your charts and double check what those are. Make sure they make sense in that case. And then you'll have some user interface or functionality issues. And this kind of can come down when you are using an incompatible extension or add-on that could be causing the problem within your browser. So you could have some missing UI elements, or the product just stops responding completely. If you're missing those kind of features, try disabling some of the extensions that you have loaded in your browser to get them to resolve. Another thing I've also seen is misconfigured join configurations. So, one or more join configurations is incomplete. You'll have some type of join key that's missing between the tables that you're trying to join. And that is going to be a blocker for some of the problems that you're going to see with Looker. So I double check your keys are correct. And then missing or incorrect data source connections. This again could come down to example errors or symptoms with your database connection string. I check your database connection string there as well for this. Another thing I'd also look into is our token usage. So we want to, if we have a token that's associated with our account, our user, we want to make sure that our report's overall token usage is within a certain threshold. So if you could have a number of quota tokens that's used by the entire report, the number of quota tokens remain available before the quota is reached. These all affect our tokens because each token only has a certain amount of operations that it can do. So in certain times, what you might want to do is refresh the token completely so you get a fresh one. And so you'll also have this quota exceeded error message. And this is just meant that, you have too many requests using a certain property in Looker. And those, depending on the property, there's a different quota for each of them. In that case, you just need to change your token or create a new user or try and reset your user so that you can have your quota reset. Now, when it comes to more complicated issues with Looker, I'd start with identifying the source of the problem. And then if your problem has just too many variables to sort of figure out what the source might be, I'd reduce the number of variables that you're trying to operate on. And I'd also make sure that the problem is reported to Google. There are times where there's a bug in the actual build of Looker that you're using. So you might want to actually report this information to your Google account executive, and they'll be able to help you out with those kind of issues. But reducing the number of variables to sort of, understand exactly what any troubleshooting step is. If you're doing too many things in the step, try and break down the problem piece by piece to get the actual source of the problem identified. And then from there, you can actually decide what to do. But it really just comes down to basic troubleshooting habits when it comes to using the Cloud Console. So that's a little bit about troubleshooting Looker and some of the error codes that you could get when working with Looker. So in this course, we've examined how to utilize BigQuery and Looker to analyze, share, and optimize data-driven insights effectively. We did this by exploring BigQuery data public sets, navigating the UI and command line interface, replication options for data sets and creating a data set, BigQuery tables and views, routines, connections, and search and vector indexes.
importing data, batch load options, publishing data sets for sharing and pricing models, and optimizing costs. Looker and Looker Studio, creating and sharing reports and the costs of using Google Looker service, and troubleshooting BigQuery and Looker. In our next course, we'll move on to explore the role of a pub sub in a data pipeline and the process used to implement pub sub correctly. Managing the resources is not unlike unlocking the doors of your own store, where every lesson on cost management and resource optimization adds a means your business can stay open another day, serve another customer, and become a profitable business operation. In this course, I'll cover the intricacies of cost efficiency and resource management in the Google Cloud Platform, explore the art of balancing expenses through hands-on lessons in counting GCP costs, orchestrating resources in data clusters, and automating workflows with Cloud Composer or workflows. I'll also delve into the creation and execution of directed acyclic graphs, or DAGs, for Cloud Composer, learn to fine-tune BigQuery processing, and master the nuances of workload management for BigQuery. This course is designed to empower you with the knowledge to navigate the GCP landscape with confidence, ensuring optimal performance and cost effectiveness. This course is one of a collection that prepares learners for the Google Professional Data Engineer exam. In this video, we're going to identify what costs can be minimized while we still achieve business needs when we're using Google Cloud Pricing and Google Cloud Platform. Let's first understand how the GCP pricing works in general. GCP pricing kind of works similar to some of the other cloud providers that we've seen, where they all offer something known as a free tier. Now, this free tier is just meant exactly like a trial for some of these services. It has limited resources, and we use these free tiers to test out various services completely for low cost, zero cost. So it's all free. There's also another model that we have within Google Cloud that's called pay-as-you-go. This means that you're only going to be billed for the actual resources that our code is going to be using when it's running on some of these resources. So I'll only pay for the things like the computing, the storage, and other resources that I consume within a billing period. Another thing that I'll see that's offered with Google Cloud Pricing is known as the discount. Now, they offer what's called sustained use of discounts for things like virtual machine instances that run for extended periods. So if I choose to run a virtual machine for a longer period of time, my per hour cost is going to automatically decrease, so I get the best value for my money. Now, the interesting thing is that with these discounts, you'll notice that you can commit them. For the longer you have them turned on, you're almost purchasing them in bulk. The per hour cost is going to decrease on their own. Now, GCP will offer things like committed use discounts, where we'll have a specific amount of resources, such as virtual machines, and I reserve them for a 1 or 3 year term. And then what happens is as they're reserved for that period of time, I have significant discounts compared to as the pay-as-you-go rate. So if I know exactly what kind of machine I need, what I'm trying to build, what hardware resources I'm going to use for that machine, for let's say it's a virtual machine, I can then reserve them for a 1 year or 3 year term. And the longer I reserve them for, the lower my rates will become. Now, here are some cost considerations that it comes to when working with Google Cloud. One of them is known as the networking cost. Now, this means that, we're going to be transferring information into Google Cloud, but we're not charged for that. So any incoming networking costs, it doesn't matter. The networking costs that come out of our Google Cloud to the internet or across the network, these additional egress and ingress data expenses are incurred if the application experiences high traffic or involves significant data transfers. So anytime I'm transferring data from one region into another cloud provider, for example, that's going to involve taking the data that's stored in Google Cloud and sending it over the internet to another location that's not within Google Cloud and not within the same region within Google Cloud. And so that causes networking bandwidth there. Now, that cost is going to be associated based on how much we choose to transfer over. Now, computing resources with virtual machines, this all depends on the type, the configuration, and the duration that I'm using that virtual machine for. This all significantly impacts the cost. So if I'm using high performance virtual machines or more significant instances with more resources, such as more CPU, more RAM,
those are obviously going to increase the cost as well. We also have something known as storage resources. Now, storage resources are things like data storage and data transfer, and we'll use things like load balancers and networking services. Let's start with data storage. The costs are influenced by the amount of data that's stored and the type of storage. So if I'm using standard or cold line storage, that's going to give me a different type. That's a different rate of cost for storing data. And how long am I storing this data for? That matters. Data transfer is another one. Expenses are incurred for transferring data within and between GCP and external networks, so I have to manage that. If I'm using load balancers and other networking services, those expenses can be affected using networking services like load balancers or premium network tiers that matter. So anytime I'm using a load balancer, it's going to increase my costs as well for my services. Now, there's also services and application programming interfaces or APIs. Now, these are charges that are incurred based on the specific GCP services and the API that's used. So if I'm using more services, they increase associated costs this way. We also have things such as data processing. So these are costs that are influenced by the quantity and complexity of my data that I'm processing. So let's say if I'm using BigQuery queries to transform my data, or I'm using Cloud Dataflow to do some data transformation, those all count as how much data am I processing and how much am I using these serverless services, and am I going to, the more complex the processing task, the more resources that processing task is going to use, and the more cost that's going to be incurred. Now, here are some cost considerations that I like to use. I like to use monitoring and logging. So this is where you'll notice that costs are going to be associated with the amount of monitoring and logging that is data generated. So if I'm using services like Google Cloud Stack Driver, those are going to be increasing my costs. If I'm using different licenses and software, like Windows Server licenses or extra software components, those can also add to the total expenses of my virtual machines. Also, the location of the resources. Certain regions have region-based pricing, so the cost can vary depending on where I store the virtual machine or a database or whatever service I'm using. So the geographic location where those resources are provisioned is going to matter. And you'll also notice that there's going to be infrastructure availability that can lead to price fluctuations across different locations, and so that matters. Another thing that you'll notice is you'll have committed use and discounts and sustained discounts. So if I try to select a virtual machine of a certain hardware type with a certain number of resources, if the longer I have them committed for, like almost on a contract for a 1 year or 3 year term, I get a bigger discount for using that machine. So that's great if I know exactly what my hardware use is going to be like for the next 3 years or 1 year. I can take advantage of these discounts. Now, here's some importance of cost optimization. We have things like financial performance of our tools. So this is where we need to kind of look at the financial predictability. We have things like our resource usage and performance. That matters as well. So if I'm trying to optimize my costs, I can also improve the performance of my resources, and I can fine-tune some of the resource configurations to match the application requirements more closely. Scalability is another issue. So cost optimization, I can quickly scale my operations without worrying about skyrocketing costs. Optimized resource usage ensures these scalability as my business grows. I'm not going to have unexpected expenses. Visibility is important. With cost optimization tools and practices, I get to see exactly what I'm charged for, and I get to see how my resources are scaling based on the usage and I can see where the money is being spent across each service. Now, this visibility will empower the organization that I'm part of, or myself as a project that I'm building, to identify exactly where the pain points are for the cost. And then this kind of signifies to me that there's probably some more performance enhancements that I can make on the services. And then this is going to be a continuous improvement project. So as I adopt cost optimization, it's going to be an ongoing journey. I have to consistently review and enhance the resource usage so I can organize and refine my cost management practices in the Google Cloud. Now, identifying and controlling costs is important. Remember, we're paying for what we need. That's our first step. That's important because we want to identify any idle virtual machines that are there, because if that's going to happen, I'm going to offer a range of recommenders, including things like an idle VM recommender, and it's a tool that's used for advanced analysis of usage patterns to identify any active virtual machines in our cloud. So that's actually very useful for this. We get to automate these VM schedules for cost savings as well, but I can also be familiar with the billing and the tools. so that not only am I paying for what I need, I'm identifying any idle virtual machines that I don't need, and I know that I can be familiar with these billings and tools that tracks the cost of my virtual machines. And then finally, what's going to happen is now I've got the right virtual machines I'm paying for them. I know that they're finely tuned. I want to make sure that I'm optimizing storage costs as well. So in the context of virtual machines, I'm thinking, okay, like what is one of the hard drives that I'm using? Do I need an SSD or can I pay for an HDD? What size do I expect to use for my application? This is where I need to optimize that storage cost. And this maybe involves fine-tuning the application that's running on the virtual machine so that it's a little more storage conscious about exactly how much disk it's going to be using. If I can make that application running on the virtual machine efficient in terms of storage, in terms of computational ability, I can save the cost for it running on these virtual machines. So that's one way to optimize the storage costs on the VMs. A little more parameters here when it comes to optimizing and controlling costs. When we're talking about a data warehouse, we want to make sure that we're optimizing for different data warehousing tools. So there's best practices when it comes to building a data warehouse where it involves things like partitioning and clustering of data sets. So if I'm clustering tables within a GCP service, this directly applies to things like BigQuery. I can substantially affect cost and performance. So that's one way we can optimize it. Another thing that's very useful is I need to enhance query performance. Remember, BigQuery, for example, is going to take my query and it's going to, underneath the hood, assign certain computational resources to run that query. The more complicated the query is, the more computational resources that BigQuery is going to use. And the more resources that BigQuery is using, the more I'm going to be charged to run that query. So optimizing the query performance and to minimize things like data scanning by implementing table clustering, it can organize the data physically in our storage. And this leads to faster retrieval and analysis, and so less computational power is used for that query. That will also save some costs. Really important here is that we're monitoring the usage of all of these services, things like BigQuery, our virtual machines, Kubernetes engines. These all matter to make sure that we know how these services are scaling. And so this is where we're going to use proper financial operations procedures. So this is where a financial operation is just a framework that enables organizations to boost the cloud financial management. And so this is combining things like financial accountability, cloud expertise, and the technology that we use. So this FinOps practices can significantly enhance our ability to organize and optimize our costs on the GCP. And these things include things like financial accountability. And what I mean by that is we know exactly what service is causing what spike in the cost, if there is any spike at all. We get to see things like showback and chargeback, where they often include things like help our team become more conscious of their resource usage and associated costs. So you're not only calculating exactly how much money the services are burning, but you get to actually show them directly to the stakeholders that are in charge of that service. And so they give that constant feedback almost every quarter, every month or so, to let them know, like, you can optimize these services a little further, because kind of giving them that feedback and sort of, turning on these services, they may not know how much money that these services are burning. So that's step one, is to identify that they are burning a certain amount of money, and they can scale that down somehow with their applications or their configuration for that service. Here's some database and smart analytics cost optimization techniques. So we've got things like Cloud SQL. This is, again, a fully managed relational database for MySQL, PostgreSQL, and SQL Server. This is where we want to monitor the usage of this service. It comes with a monitoring dashboard, and I can validate my deployments, meets the requirements for my workload. I can optimize the resources for this service as well. And this involves provisioning the database with the minimum required storage capacity, so I need to know that ahead of time. I have things like Spanner, which is a cloud-native unlimited scale database, and it offers very high availability. Again, this is where we want to monitor our usage. We want to set alerts on our deployments to optimize our storage resources. I get to run smaller workloads on Spanner at much lower cost by provisioning resources with PU or processing units versus nodes. And so this is really important. That's one way to actually minimize the cost. And with Cloud SQL and Spanner especially, it just means that we're constructing SQL statements using best practices for building efficient execution plans. And this comes down to the schema of Cloud SQL and Spanner. How is your data actually being stored? Because if you have a properly designed schema, you can actually minimize your costs, the computational complexity for retrieving the data using a query. Now, Bigtable is another one. This is a wide column. It's a NoSQL store for large-scale, low-latency workloads. So we can analyze things like usage metrics to identify opportunities for resource optimizations. We optimize resources so we can help ensure things like our CPU and disk usage that provides a balance between latency and storage capacity. And we want to evaluate this node count and size of our Bigtable cluster is important. We want to maintain performance at the lowest cost possible, and we're going to programmatically scale our Bigtable cluster to adjust that node. Now, really, when it comes to Bigtable and any of these data storage tools, it's important that we understand that HDD storage costs less than SSD, but it has lower performance. So SSD is the faster drive, and that's typically used for things like in production. But if this is maybe internally facing, HDD could have lower performance. You might be able to get away with using a lower performance drive. Now, the thing is with BigQuery, this is a serverless and highly scalable and cost-effective multi-cloud data warehouse. Really, when it comes to optimizing our resources, it all comes down to the data set level because we don't actually control any of the hardware that BigQuery is spinning up to run our query. So we want to set up our data set level, our table level, or our partition level expectations for our data. And this is going to be based on our compliance strategy. We want to limit our query costs by restricting the number of bytes that are billed per query. So accidental human errors, where somebody is actually running a complex query over a full data set, which may be a human error. So what I can do is I can enable cost control at the user level and project level so that no one can actually run a very complicated query on a certain amount of data that I set as that limit. So that's a way to actually prevent runaway costs. Data flow is another fast and cost-effective serverless service for unified stream and batch data processing. Again, when it comes to monitoring our usage, we want to increase the visibility into throughput and CPU usage by looking at its dashboards and optimizing the resources. We want to use batch pipelines so we can reduce the CPU, memory, and persistent disk storage consumed on the worker virtual machines by using what's known as a data flow shuffle. So there's all sorts of different data flow techniques that will reduce the cost for data flow. The thing is that we can't go into all of these techniques because they're very data flow specific. So things like a data flow shuffle kind of goes outside the scope of this video, but just know that they do exist to actually reduce the cost. Dataproc is just a managed Apache Spark and Apache Hadoop service for things like batch processing, querying, streaming, and even machine learning. So we want to make sure that we follow certain best practices. Obviously, we want to choose the machine types that are appropriate for our workload. We don't want to over provision our machines because that's actually going to cost us some money. So we need to understand exactly what our code is doing, what our Spark code is doing, or our Hadoop code is doing on the machine types, and understand what resources they actually need and provision them accordingly. And so this is what's going to affect the cost mainly for Dataproc, because this is a service that we're going to have to choose what hardware is going to be needed for our Spark code and our Hadoop code. That's a little bit about some of the services and some of the issues that we are seeing when it comes to reducing costs across multiple services. In this video, we're going to talk about controlling resources in Dataproc clusters and identify whether a persistent or ephemeral cluster is a better solution for our particular business use case. Let's first understand the issues surrounding a persistent cluster model. And remember, with Google Cloud Dataproc, what we're working with is a managed service for big data analytics for Hadoop, Spark, Hive, and pretty much over 30 open source engines and frameworks that are available to be run on Dataproc. So there's two common application architectures, and one of them is called the persistent cluster model, and the other is called the ephemeral cluster models. And there's pros and cons with using one of them. Let's first understand what's going on here with the persistent cluster model. So the persistent cluster model represents single points of failure. Okay, so in the persistent cluster model, a cluster is created and we keep that cluster running. This is as a resource pool that's shared by many jobs for a very long time. Now, users will often enable features, things like auto-scaling, to increase our reliability. So persistent clusters, they're what's called a stateful system. Now, the problem is that they're more prone to trouble. So they are an in-cluster system. If they were to fail, imagine if you had one cluster that's running and it fails, we can't bring it back up, your whole service goes down. So users coming from an on-premises, the persistent cluster model will be a natural lift and shift to the cloud. But when it comes to this, the model will often represent a bad architecture choice in the cloud. This actually is going to lead to emergency situations in the future, and they become very complex to repair because of this. So this single point of failure is really not something you want to worry about, because imagine when your disk gets filled up with logs and temporary files, and this could lead to job failures. Now you have to go in there and try and figure out what caused this single point of failure, this cluster, to bring down your whole application. Now, they're very difficult to repair, recreate, and upgrade. So it's not something that we want to lean towards. Now, there are some more issues that are surrounding persistent cluster models, such as the job performance can be unreliable. It can be unpredictable. You don't know exactly how the cluster is going to perform on a single job. And so one run of a job can be several times slower than another run of the same job. And so this can be a big issue for critical workloads. And so you may have to have future support may waver. So what you'll notice with Dataproc, our persistent cluster model isn't going to be running for months or years. It can become unsupported over time. And so when issues happen to unsupported clusters, this will be difficult to get support from a Dataproc team. Now, here's some reasons why you should use persistent clusters. There are some advantages. Their costs are predictable. I know exactly that if I run this machine for this amount of time, my cost is going to be this much per month. So persistent clusters have more predictable costs if auto-scaling is disabled. So some users with a strict budget might prefer to use this, and this might actually make sense if you're building an application that's more internally facing and less customer focused. You might get away with doing that. So things that have non-mission critical workloads, this would be great. So if you're building something for a test environment, this is a way to save some money to do so. You'll have things like an on-premises lift and shift. It's very easy to move things from on-premises and put it directly in the cloud. It's a natural solution to this, right? So when migrating to the cloud, it's easier for us to keep the same model and finish the migration first. And then what we can do is we can gradually switch over to the ephemeral model as needed. And it's great for things like streaming workloads. So for streaming workloads, if you're using things like Spark Streaming or Flink, the clusters have to be long running, but the same principles still apply. When we're preferring a job clusters over shared clusters and avoid persistent in-cluster states, this matters. Now here's some benefits of an ephemeral cluster model. So one of them is that it doesn't represent a single point of failure. Ephemeral just means that if the cluster goes down, no problem, Dataproc will create another stateless system where it doesn't have to remember what it was before, just brings it back up. So things like your Docker containers. If a Docker container fails, we can use the Docker image to just create another Docker container. It's not really going to affect anything. And so we get reliable job performance this way. They're more consistent and they're more predictable because there are no resource contentions in ephemeral clusters. I know that job performances are more consistent, and this is what's going to be great for critical workloads. Now, some more benefits includes things like effective for individual jobs. You'll notice that the ephemeral clusters are great for just single jobs that need to run, and they don't need to run over and over again. So you can choose high memory machine types for memory bound jobs, or I can even use a local SSD for jobs which involve lots of shuffle. So their hardware and software configurations will allow ephemeral clusters to optimize configurations for every job that we're using. And when I look through the ephemeral clusters, they're more up to date as well compared to the non-ephemeral ones. So Dataproc has what's known as a weekly release. So for a new image that gets created, it includes things like bug fixes, security patches, new features, and performance optimizations. I know that the ephemeral clusters can be easily created with these new versions to get the updates, and it helps avoid the clusters to become unsupported like we saw with the non-ephemerals. Now here are some benefits of an ephemeral cluster model. Again, this is about zone resource stockout adaptability. So ephemeral clusters adapt to zone resource stockout much better. So transient resources with stockout can happen to zones when a persistent cluster needs to scale up because its zone is fixed. Scaling up might fail due to resource stockout in the zone, but ephemeral clusters can leverage what's known as the auto zone placement. So if it can't find the resources that it needs in the zone that it needs to be created in, it'll move over to another zone that has the hardware in it. So that's very useful. You'll notice that they also have lower costs. In persistent clusters, users will get charged when they are idle, even when you're not using them. Whereas with the ephemeral clusters, you only pay for what you use.
So they're created when you need them on an on-demand basis. And then when you're done with them, you can delete those clusters and you won't be paying for them. So this overhead of cluster creation, which is just usually a few minutes, is very minor compared to the job duration that you'd be running in. So that's a little bit about some of the benefits when it comes to an ephemeral cluster model versus a persistent cluster model. In this video, we're going to compare and contrast how workflows in Cloud Composer can be used to orchestrate pipeline tasks. Let's first understand what is orchestration. You've probably heard this term multiple times. Orchestration in general is a computing term, just refers to the automated configuration, coordination, and management of any computer system or services. So if we're talking about a service-oriented architecture like the ones we see in cloud computing, this can range from simply executing a single service at a specific time and day to have a more sophisticated approach of automating and monitoring multiple services in conjunction with each other over long periods of time. And this allows us to have the ability to react and handle failures as they crop up. It really just comes down, when we're talking in data engineering, it's just a way for us to coordinate many different services and workflows so that we can prepare, ingest, and transform our data. And it can go beyond things like data processing. So this is great when we have a workflow to train a machine learning model from our data. We want to process our data, clean our data, and send it over to a training pipeline. So this training pipeline is the orchestration piece, from processing our data and sending it over to a pipeline that is going to actually train the machine learning model. That needs to happen in conjunction in a certain sequence so that we can actually train the ML. Now, what we're going to talk about in orchestration in Google Cloud, there's a few different services and terms that we should be aware of. Google Cloud will offer a number of tools and services for orchestration, and one of them is known as Cloud Scheduler. This is great for scheduling driven, single service orchestration. You want to bring up a virtual machine for a certain thing, for a certain operation, you can do that with Cloud Scheduler and turn it off after you're done. It's great for things like workflows. If I'm trying to use multi-service orchestration, such as retrieving data from BigQuery and sending it over to Vertex AI to do some training, that matters. We can use our workflows. Now, Cloud Composer is orchestration for all of our data workloads. And this is great service for when we're trying to create multiple services in conjunction with each other so that we can design a ETL framework or ETL pipeline. Let's start with Cloud Scheduler. Cloud Scheduler is just a service for scheduling the execution of a single service on a recurring schedule. And it's great for us to use a cron job or cron scheduling for this. It's great if I have a single piece of code that needs to run at regular intervals, say the first of every month or the last day of every month to do some type of analytics. I can use a cron job or cron scheduling to take this code and run it once per month. Workflows is a service for orchestrating multiple HTTP-based services into a durable and stateful workflow. Now, these services could include things like creating a compute engine, for example, and then tearing it down later. I can do that as well. Now, this is unlike Scheduler. Workflows has sophisticated logic that lets us manage the execution of multiple services as part of a wider workflows. And so this is where I can automate some of these HTTP-based services. Now, I can either use YAML or JSON to sort of define what this workflow will be, and I can also manage these multiple services directly in workflows themselves. So it's great for chaining microservices together. I can automate some infrastructure tasks and starting or stopping a virtual machine, for example. I can then integrate reliability with external systems, and it's very easy for me as a central source of truth for service integrations. And I can improve things like observability and error handling in services so that if my virtual machine fails to spin up, something happens. I can define what that thing happens. So it's very useful in service-oriented architectures. So if you're focused more on engineering data pipelines or data processing, then we should use something known as Composer. Now, Cloud Composer is really important for when we're building data pipelines. It's a fully managed orchestration service. I need to manage and monitor the workflows in the pipeline, and I can automate them to run periodically. This pipeline workflow and management and monitoring is important. So this is going to be built on Apache Airflow, and it helps us schedule and monitor these pipelines. And I can even span hybrid or multi-cloud environments. So it doesn't have to be directly tied with Google Cloud. It can be an on-premises system, or it could be another cloud provider such as Amazon Web Services. Here are some key advantages of using Cloud Composer. One of them is that I can benefit from things like Apache Airflow without any management burden. I have enterprise ready and some security features as well as some auto scaling features that can be used as more data is being pipelined into the Cloud Composer. I can actually leverage an auto scaling tool that will assign more computational resources so that it's better able to handle the load. Now, here are some Cloud Composer functionalities that are there. So if I'm working in data analytics, a workflow could represent a series of tasks. So this could involve obviously ingesting, transforming, analyzing, or utilizing data. That's a lot of different steps to worry about. So in Airflow, what happens is that we create workflows that are created direct acyclic graphs, or DAGs. Now, all this is just a collection of tasks that we want to schedule to run. We want to run task 1 first, which could be ingesting our data. Task 2, which would be transforming. Task 3 could be analyzing our data. And this is going to reflect the relationships and dependencies between these things. We're going to take the output from our ingestion and send it over to the transformation. After the output from our transformation, we're going to send it over to the analyzing step. This structure is what's going to be designed with our code, and it's so that we ensure that each task is executed at the right time. It doesn't make sense for us to transform our data before we've even ingested it. So we have to have it in the right order, and the DAG is what's going to ensure that that's done. So everything is going to be timely, ordered execution with issue handling in between, so that if something happens at the ingestion step or the transformation step, we stop the DAG and we don't send it over to the subsequent steps afterwards. Now, here's where we can have some running workflows in Cloud Composer. After I create a Cloud Composer environment, I can actually run any workflow that my business requires. So I can create this Cloud Composer environment for the first step. I can then run my workflows that I need. And the Composer service is based on distributed architecture. And so those workloads can be scheduled. And I can even run them on things like Kubernetes Engine if I need to, or any other Google Cloud services. And if the workload is small enough, I can get away with running it on a virtual machine. So I can schedule these workloads at a specific time. I can start a workflow when a specific condition is met if I choose to. And so let's say an object is saved to a storage bucket. No problem. As soon as that object goes into that bucket in that folder, we can trigger this workload to start, retrieve that data, and run the workflow for it. That condition that's met is called event-based, or you can have them on a schedule-based or temporal-based. So you can run the workflows at the end of every month or a certain day of the week. You can do that. And it also offers built-in integrations with things like BigQuery and Dataproc. So that's going to be also enabled by provider packages from vendors. And I can even run applications that are on-prem or another cloud provider if I choose to. There's a few different built-in integrations and provider packages, including open source ones, that we can actually utilize directly in Cloud Composer. Now, let's take a look at Composer and workflows and see where we might use one or the other. So Composer is great for multiple service orchestration, and Workflows is also great for multiple service orchestration. So they're similar in that regard. But with Composer, we orchestrate our data transformation as part of an ETL or an ELT, or extract, load, transform, or any type of data engineering operation. Whereas with Workflows, it's great for us to orchestrate HTTP-based services built with things like Cloud Functions, Cloud Run, or even an external API. We can orchestrate our batch workloads with very little latency, and we can orchestrate latency-sensitive use cases in our workflows. Now, with Workflows, it's completely serverless. But with Composer, we have to specify the number of workers for our Composer environment. But we can also turn on auto-scaling to sort of match the load of the data that we're sending into our pipeline. It's all up to us. But Workflows, we don't have to worry about the hardware at all. Google will handle that workflow for us, and we'll pay for what we need only with the workflows. Okay, so that's a little bit about the difference between Composer and Workflows and how we can actually use them for data engineering or any type of orchestration for HTTP-based services.
In this video, what I'm going to do is I'm going to create a simple DAG or directed acyclic graph, and I'm going to run it with Google Cloud Composer. And there's just several steps that we're going to have to talk about here. So the first thing is I'm going to talk about this DAG that I've created using Airflow. Now, what I've done here is I'm going to be using a Python script, a very basic one, to run a hello world command using bash. And there's just a couple of things that we're going to actually be using to set this up. So one thing I'm going to do here is I'm going to first install the Airflow operations using pip. So this is going to be pip install Airflow. And so this is going to install the packages necessary for me to actually run this information. So I'll be importing some Airflow tools and then creating this script and then uploading it directly to Google Cloud Console to use orchestration tool, the Cloud Composer, and then it'll run on a schedule that I choose. So what I'm going to do is I'm just going to create some default arguments for the DAG. So it's just a basic dictionary. So I'm saying the owner is going to be Airflow. I'm going to depends on past is false. I'm going to give it a start date of 2024-0101. I can give it an email on failure as false or email on retry as false. I'm going to ask it to retry once and then wait 5 minutes if it has to retry. The next thing I'm going to do here is I'm going to now define the DAG. So this is where I can actually say, use the DAG tool that I've imported from Airflow. So all capital DAG for directed acyclic graph. First thing I'm going to pass in as an argument is the name of the DAG. So this is just going to be hello_world_DAG. And then there's going to be default arguments where I can specify the default args from before. And now I give it a small description that just says, it's a simple hello world directed acyclic graph. And I can schedule this interval to be days is equal to 1. So it'll run every 1 day. And then I can define the task here with the bash operator. So saying that the task ID is going to be print_hello. This is the bash command that we're going to be using, which is echo hello world. And then the DAG that's actually containing the default arguments and some scheduled intervals is going to be set as DAG is equal to DAG. Now this is T1 is going to be our actual task. That's what's going to be defined and run by Airflow. Now what I'm going to do is I'm going to take this Python script and upload it to my Composer environment. So before we can do that, I am going to use my Google Cloud Console to go to the Composer environment. So the first thing I'll do is I'll go to Composer, call Cloud Composer, and you'll see right here it says Managed Workflow Orchestration Service. Now what I want to do, I'll be met with a page that might ask me to sort of enable some APIs. Perfectly normal. Go ahead and just enable those APIs to get started. You'll have to then be met with a page that's going to be completely empty and it says you're going to have to create an environment. But if there isn't a Cloud Composer environment already created for you, I'll show you how to create one of your own. So on the top left, underneath the search bar, you'll see that there is a create and a down arrow. Go ahead and click that down arrow and then click Composer 2. Composer 3 is still in preview mode, but it offers serverless tools. Now what I'm going to do is just use Composer 2, and this is where I will be met with this page. So I'm going to go ahead and provide a name for my system. So I've already created one of these. I'll just walk you through some of the settings here. So the name and the location is important. The image version of what Composer I will be using and what Airflow version I will be using is going to be selected. There's either 2.91 or 2.7.3. I've used 2.91. That's the latest version of Airflow. So this is going to be what's going to be running our tool in the cloud. I've already created a service account for me, so I'm going to use the default one for compute for this service account. I can add a label for cost tracking later. And standard resilience is fine, but if you have high resilience, it's just a way for if you are using this in, let's say, a production environment, I recommend that you use the high resilience. It'll cost a little more in environment resources, but it is for your customer-facing tool. But in this case, since we're just using this as a kind of a test, we can just stay with the standard resilience. Now, there's environment resources that we can use, such as, the scheduler is going to be using a certain number of virtual CPUs, certain number of memory. Now, it makes it very easy for me to actually get the tools that I need, whether I use medium, large, or custom, where I can actually create the number of schedulers and how much CPU and memory each of these components will need, part of the core. For now, I'm just going to leave it as the small size, and then I can keep everything else as the default for network configuration, and now I can just click the button here that says Create. Now, I've already created mine, so I'm going to click Cancel, but yours will, if you click Create, it'll take a few minutes for everything to pop up. You'll know that it's all ready when this stops being a circle, and underneath the state, you'll see a green check mark. After that's completed, what you want to do is you want to go ahead and click the name of your environment. So mine is called my-composer-environment, and you're going to be met with a page that looks like this. There's a few different tabs here, so it's a little confusing at first to navigate. But the first thing I would do is up at the very top, there is a section called Open DAGs folder. Now, what this is going to be a Google bucket that is going to be attached to the Composer environment. This is where I will take that script that I wrote earlier called my_dag.py, and I will upload it directly into this bucket. So I'm going to click Upload Files and place it in here. After that, what's going to happen if I go back to my other tab, I can click the other button next to Open DAGs folder that we just clicked, and it will open Airflow UI for us. Inside of the Airflow UI, you will see a page that looks a lot like this. It might take a few minutes to see your new Hello World DAG pop up, but what's going to happen is that you will have all of these directed acyclic graphs. One of them is already there by default. It's called Airflow Monitoring. You want to keep that enabled. This is what allows us to monitor our Airflow server. And one of them is just uploaded, and it will be in the unpause state, and that is going to be running, and it'll be running this Hello World operation over and over again. So right now I've left it in the unpause state, but when I want to turn it on, I will just click the check mark here, this little switch, and my DAG is going to be running over and over again. If I click inside of Hello World DAG, what'll happen is you'll start to see all the pieces of Hello World, this DAG that was running. So you'll see some of the details, such as how many times it was run. You'll see some of the DAG summaries, such as the total number of tasks, one bash operator is being used. It tells us all sorts of the metadata that we've created for this DAG inside of our code. And what's interesting is that you can actually see a graph of your DAG. So from left to right, you can see, okay, this is the only operation that my DAG contains. But if I had another operation, I can say this is my first operation. And then there's a little arrow which will point to the next operation, and it'll do this in sequence. So this makes sure that I'm not going to be doing anything before this is completed. It's a way for us to have some type of control structure in some code. And this is very useful if you imagine if we have an ETL, maybe I'll have an extraction operator, a transformation operator, and a load operator. Now, I obviously don't want to load any data until my transformation operator is complete, and I don't want to transform any data until my extraction operator is complete. This is the idea of what the DAG will do, is it'll make sure that things are going to flow in sequence. Now, I can actually look at the code itself by clicking the Code tab, and you can see here that this is the same code that we were showing earlier in my VS Code window, and it's all right there, and it runs perfectly fine. Now, I have all of this run, and it's quite easy for me to actually get this going. And so now, this is really all we need to do to sort of get our DAG. I can turn it on anytime by going up at the very top left and clicking this blue mark, and then my operator will start to run. And that's how we can actually create a simple Airflow DAG and then run it inside of Cloud Composer. In this video, I'm going to identify the costs and the benefits of selecting between interactive and batch query jobs when using BigQuery. Let's first understand how the analytic workflows work inside of BigQuery. So with analytic workflows, we have these things called ad hoc analysis. Now, what this means is that we're using BigQuery and Google SQL, which is the SQL dialect that's utilized inside of a BigQuery tool, to support any type of analysis that needs to be done on the fly. So we can run queries in the Google Cloud Console or through third-party tools that can actually integrate with BigQuery. So we can use an ad hoc analysis there. There's also a tool for us to use in geospatial analysis. So BigQuery will use geography data types and Google SQL geography functions to let us analyze and visualize geospatial data. Now, this is really useful for when I'm working with exactly some type of latitude, longitude pairs, or I'm working with position time pairs that come from like a cell phone, GPS, or a satellite, for example. And I also have machine learning tools that are useful when I'm using BigQuery ML. This is where I can use my Google SQL queries to let me create and even execute some machine learning models directly in the BigQuery tool. And finally, I can also utilize some type of business intelligence. BigQuery has a business intelligence engine, which is very fast and has an in-memory analysis service that allows me to build rich and interactive dashboards through an HTML and reports without having any type of performance happening in the engine.
And it has things like scalability, security, and data freshness built into these dashboards models that I'll create through the BigQuery BI engine. Here are some data sources that can actually integrate inside of BigQuery. Number one is we have the data that's stored inside of BigQuery can be loaded into BigQuery for analysis. So I can actually generate data by using what's known as a data manipulation language, similar to any other relational database management system. So we have DML statements, or I can even write query results into a table. And then I can query that data stored in either a single region or multi-region locations. But I can't run a query against multiple locations. So if I have a single region location and the other is a multi-region location containing that single region location, it becomes a little bit of a problem. So I have to be mindful of where I'm storing the data, but it is possible that I can actually use just some basic data manipulation language statements to store them. I can also reference external data, so I can query some various external data sources, such as things coming from the Google Cloud Storage buckets or services like Cloud Storage, or I can use a database service like Spanner or Cloud SQL, and those can actually be queried directly inside of BigQuery. There's also multi-cloud data that's available, so I can query data that's stored in other public cloud data sets, such as AWS or Azure, so it's actually able to interface there. And I can also query public data sets. So if I don't have my own data, I can analyze any of the data sets that are available in the public dataset marketplace that's offered directly in BigQuery, and they have multiple sources, such as the United States government and a few different sources as well that can have some type of demographic information or demographic data that can be public. Now, how do we actually run these queries? So queries here are just interactive query jobs. So it's similar to any type of relational database management system that we've been working with. I write my SQL query in the editor, and then I'm about to run it. Now, what happens is that I'll take those BigQuery SQL, and it will run as an interactive query job. So as I run a query, I can have interactive versus batch queries. So in BigQuery, I can run two types of queries. So there's interactive query jobs, which are jobs that BigQuery will run on demand. So I go into the editor and I type my SQL, and then I will run that code. Or I could have batch query jobs, which are jobs that BigQuery wants to run until the idle compute resources are available. So I kind of schedule it, and then when it finds all the resources that it needs to actually run this batch job, it'll execute that query. So it's something that more of an asynchronous approach rather than a synchronous approach. Now, BigQuery has two SQL dialects. We have Google SQL and Legacy SQL. So Google SQL is the preferred dialect when working with BigQuery. It builds on top of Legacy SQL and has some BigQuery-specific commands that are useful for us to use with the BigQuery tool. We can use the Legacy SQL similar to what we would expect with any other relational database management system, but you'll notice that with BigQuery SQL, it'll support SQL 2011, and it'll include extensions that support geospatial analysis and some machine learning workflows that we might need. Now, there are some required identity and access management roles when it comes to working with BigQuery. So we need to make sure that we have the permissions to run a query job. So before we do anything, we have to make sure as the administrator, or we have to ask our administrator to grant us the following IAM roles. So one of them is called the BigQuery job user, and this is what's going to allow us to run jobs in the BigQuery. And we have BigQuery data viewer, and this is so that we can look at my query references. So to query views, you also need this role on all underlying tables and views. And it's great if you're using authorized views or authorized data sets. And so it's really important for us to have these permissions in place for us to be able to view the data or to run some type of job, such as an SQL job to return some data. Now, there are some methods for running BigQuery jobs. The most common one is to just jump on the Google Cloud Console, go into BigQuery. That gives you an in-web interactive editor there that you can actually just run your data and hit enter, and it'll run the code and then spit out some tables. You also have the BQ command line tool, which allows you to take a BigQuery command line tool that's installed with your Google CLI, and you can actually run your query there on the actual data set, and it'll return the information in your terminal or in the command line, and so it'll be a table that you can actually read. Now there's the REST API approach as well, so I can actually run this code using the API that's actually attached to BigQuery if I choose to. And then there's also BigQuery client libraries, which come in Python and JavaScript, so that I can actually write some code and then programmatically interact with BigQuery datasets by writing my SQL query as a string in Python and then sending that over to the BigQuery client library for Python to actually run the job for me and retrieve a dataset programmatically in Python. Now we also have interactive query jobs that I want to discuss. So we've got things such as the run by default and as soon as possible. This is what an interactive query is. So again, this is the synchronous approach rather than asynchronous approach. So I'm going to write my query in the console, for example, go ahead and hit enter, and this will run as soon as it has the resources. So BigQuery will dynamically compute the concurrent query limit based on the resource availability and run the code for us. So it's going to dynamically compute this limit, and then additional queries will wait in the queue as if we've overcome the limit. So this is important. So as we know that we have to make sure that how much resources are we going to be running at the same time to run this query. So the more queries I run in succession, it just holds in a queue until the first one is finished and the hardware resources unlock. Now we've got the BigQuery cost considerations that I want to discuss. So we've got things like batch loading. So this is where I can load source files into one or more BigQuery tables in a single batch operation. It's quite cheap to do that. We also have streaming inserts, so I can actually use stream data from one record at a time or in small batches, and then I can actually use the BigQuery storage write API or the legacy streaming API to actually take those results of those inserts and actually store this information one at a time. Now the streaming inserts is going to cost you about a penny per 200 megabytes of data, and the BigQuery storage is going to cost you about 2 cents per 1 gigabyte. And again, this is so you know that the first 2 terabytes per month are free, but please keep in mind that you will be paying about 2 cents per 1 gigabyte after that for all the data that you'll be storing batch loading. That's just a little bit of food for thought when it comes to BigQuery cost considerations and exactly what interactive query jobs and how the methods for running these interactive query jobs vary. In this video, I'm going to describe how BigQuery workload management enables control over our resources. Let's talk about how workload management works in BigQuery. So all this does is it allows us to control resources and features that are available for things like data analysis so that all of our organizations can utilize it. And it allows us to define our billing models as well so that we make sure that we're not going to be running up the bill when it comes to using BigQuery. So we have things like compute capacity that are measured in slots, and they can be purchased in reservations, and we can actually have them on a contract for 1 year or 3 years. So we can have a commitment for those resources if we know ahead of time what we're going to be using. And this allows us to then assign these across our organization to perform different jobs that we need. Now, the way that BigQuery billing models work is there's 2 different ones. We have the on-demand pricing, and this is by default. This is what you'll be using. So you're billed for the data scanned by your queries, and you have a fixed per project query processing capacity, and you only pay for the number of bytes that are processed when you use them. And we also have the capacity-based pricing. This is where we can purchase dedicated query processing capacities at a discounted rate. So this is where I can say, okay, my capacity is measured in slots, and then I can allocate certain slots to workloads for parts of my organization. And this capacity-based billing is great if you are thinking of commitments. So you're saying, okay, I want to have a consistent level of processing capacity for a 1 or a 3 year period. And then what happens is because I'm committing to that period of time, I have a discounted price. So there is no charge for bytes processed when using the capacity-based models. And so there's certain advantages, such as predictability. So the capacity-based slots allow for more consistent monthly fees. And you have things like centralized purchasing. So I can purchase and allocate slots for the entire organization rather than for each project that uses BigQuery. So the whole organization gets a certain number of slots, and I choose to dedicate them to different projects as I see fit. Now, this is where we can work with some billing models, right? So we have, billing is specified on a per project basis. So maybe I want to run some workloads with an on-demand pricing and others with capacity-based pricing. So I can combine my billing models if I choose to, but they're on a project based. So as the billing model is specified per project, this would require you that you use multiple projects for our query jobs. And so this means that we can actually combine our models, but we also have to separate our projects inside of Google Cloud. And so that may or may not be feasible depending on how you have your cloud set up, but it's an option if you choose to use that. Now we have things such as our processing capacity. Now I've kind of alluded to this before, as I said that these things are measured in slots. So processing is measured in these things called slots. Now what are they? They represent virtual CPUs that are used to query our data. So in general, we have access to more slots. It allows us to run more concurrent queries, and your complex queries can run faster. But there is a catch here. Since these are virtual CPUs that query our data, the more virtual CPUs that we have, sure, our system is faster, but we pay more for that. So we have to make sure that there's a bit of a trade-off here. So your queries can run within that capacity, and you pay for that capacity continuously every second it's deployed. So if I purchase 2,000 BigQuery slots, my queries can aggregate are limited to 2,000 virtual CPUs at any given time. So you have capacity until you delete it, and you can pay for 2,000 slots until you delete them completely. Now that's really how these slots will work. Now the other way of handling it is we use these things called reservations. Now reservations just allows us to have certain allocations for our job pools. Now I can allocate these to jobs in pools called reservations. Now this just allows me to assign slots in ways that make sense for the organization. So maybe I'll create a reservation, I'll name it prod for production workloads, and a separate reservation named test for testing workloads, so that the test jobs don't compete for production workload resources. So that's just an example of how I would have two different pools or reservations in place. Now this allows me to have some limitations and assignments on each reservation. So maybe I only want a certain number of slots for my testing reservation. So I can actually give that limitation and assignment to that testing one. So it'll be much smaller than the one that I'd expect for production, since that's going to be affecting customers. So that's just a little bit of how these reservation assignments will work. So I have to make sure that I assign one or more projects, folders, or organization to that reservation that I'm attaching it to. Now let's move on to understanding how workload management works. So when we're working with workload management, there's a couple things that we have to make sure that we understand. There's going to be organizational workloads. Now, this means that BigQuery are based on an organization scope resources, and so they're typically owned by a project, and they can't be used by other projects within the organization. So we'll have things like department management as well that's built in, and so you can use BigQuery reservations to isolate our committed capacity across workloads, teams, or departments, and I can create additional reservations and assign projects to those reservations. Remember, all a reservation is just an isolated pool of resources with the advantage that it can take advantage of idle capacity. Now we'll have things such as regions and reservations as well that's in place. So not only am I applying these physical resources to a certain project, but I'm also deciding where those physical resources will be. So then we can actually have things like capacity commitments. And so this is where we'll have a commitment is just a purchase of slots for a specified period of time. The longer I have this period in place, the more savings I will have. So there's a 1 year or 3 year commitment that I can choose. So I can actually purchase in 100 slot increments up to my slot quota for my account. And I can then have them renew and expiration in place. And if I have a 3 year commitment, I can purchase a 3 year commitment, and I can choose whether to renew or convert to a different type of commitment plan after this certain number of years have passed by. Or I can have a type of annual commitment where I can purchase a 365-day commitment. Then I can choose whether to renew or convert to a different type of commitment plan after 365 days. Now, really what I can do is at the end of the day is I can actually just decide if I want to have some type of expiration in place. So after I create a commitment, it can be deleted only once the commitment expires. So to delete an annual or 3 year commitment, I can actually set its renewal plan to none in the console. And then after the commitment expires, it's just deleted automatically. So I don't actually have to have this recurring billing cycle. It's just slotted away for the certain number of years that I have it set. And then after those number of years have either 1 or 3 years have passed, then the commitment is actually canceled, and then I will be free of the contract. So that's a little bit on how the different types of cost structures work inside of BigQuery. So in this course, we've examined how to manage resources and costs effectively, automate data processing workflows, and optimize BigQuery operations for enhanced performance and efficiency. We did this by exploring GCP costs, controlling resources in Dataproc clusters, automating pipelines with Cloud Composer or workflows, creating and running a DAG for Cloud Composer, optimize BigQuery processing, and workload management for BigQuery. In our next course, we'll move on to explore how to troubleshoot and monitor cloud environments, manage resilient streaming data pipelines, and ensure high availability across distributed systems.